Somewhere in the dark between the stars, an object drifts that contains 50 times the mass of Jupiter and is barely larger than Jupiter in size. It does not shine, it does not burn with the steady hydrogen-fed fire of a true star. And yet it is not cold, not inert, not simply another planet swelling in the outer dark. It glows, faintly, at wavelengths the human eye cannot detect, with the slow release of heat accumulated over millions of years. Its surface, if it can be called a surface, hovers somewhere around 1,000 degrees. Its interior presses inward with gravity, enough to reshape matter itself, to force atoms so close together that the rules of ordinary pressure no longer apply. And still it does not ignite. This is an object that exists entirely within a boundary, not a gradual boundary, not a soft transition zone, but a precise physical threshold defined by temperature and nuclear process, a line drawn in physics, not in observation. Below that line, the object remains what it is, warm, dense, slowly cooling, permanent in its failure to become the thing it came so close to being. Above that line would have been a star, and the difference between the two is not a matter of distance, not of composition, not of time. It is a matter of mass. The threshold sits at approximately 80 times the mass of Jupiter. An object that exceeds this mass during its formation will eventually push its core to the temperatures needed to sustain the proton-proton chain, the nuclear process that powers the sun, that has powered the sun for 4.5 billion years and will power it for several billion more. The proton-proton chain fuses ordinary hydrogen, the most abundant element in the universe, at core temperatures of around 10 million Kelvin. At those temperatures, the pressure of radiation and hot gas pushing outward balances the pull of gravity pulling inward, and the object stabilizes. It becomes a star. It will burn steadily for a very long time. An object that forms with less than 80 Jupiter masses cannot reach 10 million Kelvin at its core. Its gravity is not strong enough. The inward pressure it can generate through gravitational collapse is not sufficient to bring the protons in ordinary hydrogen nuclei close enough together and fast enough together for fusion to take hold and sustain itself. The core temperatures it can achieve, real temperatures, genuinely extreme by any earthly comparison, stop short. They reach 1 million, perhaps 2 million Kelvin. They do not reach 10. The proton-proton chain, approached so closely, remains unlit. What forms instead is a brown dwarf. The name calls up something dim, intermediate, neither one thing nor another. And in physical terms, that is precisely what a brown dwarf is, an object occupying a mass range that has no counterpart anywhere in the solar system, sitting between the largest planets and the smallest stars in a category that belongs wholly to neither. The solar system contains planets and it contains the sun. There is nothing in between. Brown dwarfs are the in-between, and for most of human history, there was no reason to imagine they existed, and no way to look for them if anyone had tried. The lower boundary of the brown dwarf class is set at approximately 13 times the mass of Jupiter. This number is not arbitrary. It marks a different nuclear threshold, a lower one, the ignition point for deuterium fusion. Deuterium is a heavy form of hydrogen, a hydrogen atom whose nucleus contains one proton and one neutron rather than a proton alone. It is far rarer than ordinary hydrogen, present in only trace amounts in any cloud of gas, but it is also easier to fuse. Deuterium fusion begins at core temperatures of around 1 million Kelvin, a threshold that objects above 13 Jupiter masses can cross. And so a brown dwarf in its earliest life does burn. For a few million years, while its deuterium supply holds, it produces genuine nuclear energy from its core. The burning is modest. It generates warmth. It slows the object's contraction slightly, and then the deuterium runs out, because there was never very much of it, and the nuclear burning stops, and what remains is an object that will spend the rest of its existence, billions of years, tens of billions of years, slowly releasing the heat it accumulated during formation and that brief early pulse of fusion. Below 13 Jupiter masses, there is no deuterium fusion either. Objects below this threshold are planets, or more carefully, they are in the mass range of planets, though whether any particular object is a planet depends on more than mass alone. The boundary between a massive planet and a brown dwarf remains a subject of careful consideration among astronomers, but the nuclear threshold of deuterium fusion provides a physical anchor point: 13 Jupiter masses. Above it, brown dwarfs, defined by what they briefly can burn. Below it, planets, defined by what they cannot. Held in the mind alongside Jupiter, a brown dwarf is a strange object to contemplate. Jupiter is itself a world of staggering scale, a planet so large that the Earth would fit inside it more than 1,000 times, a world with its own magnetic field, its own storms, its own faint internal heat leaking upward from the compression of its formation. And yet a brown dwarf containing 50 times that mass would be, in terms of physical diameter, only slightly larger. This is not intuition. It runs against the way ordinary objects behave. A boulder 10 times more massive than another boulder is not merely 10 times larger in volume, but it is correspondingly larger in some sense. A star more massive than the Sun is meaningfully bigger, but in the brown dwarf mass range, adding mass does not substantially increase size. The reason is quantum mechanical. Deep inside a brown dwarf, hydrogen and helium are compressed to densities where electrons can no longer behave as they do in ordinary matter. In ordinary matter, electrons are spread widely through the volume of atoms, and adding mass to an object compresses those atoms until pressure from ordinary thermal energy, from heat, resists further collapse. But in a brown dwarf, the compression reaches a point where the resistance comes not from heat, but from quantum mechanics itself. Electrons, according to a fundamental principle of physics, resist being forced into identical states. When they are packed tightly enough, this resistance, called degeneracy pressure, becomes the dominant force holding the object up against gravity. And because degeneracy pressure does not depend on temperature, it does not increase simply because more mass is piled on. More mass, compressing the object harder, does not make it grow much larger. The object stays approximately the same size, regardless of how much more material is added, until eventually the mass becomes so great that even quantum pressure gives way, and the transition to true stellar ignition occurs. The result is that a brown dwarf of 20 Jupiter masses and a brown dwarf of 60 Jupiter masses are not dramatically different in diameter. Jupiter and a brown dwarf, 40 times more massive, might stand side by side and appear, at first, to be objects of similar scale, though the differences in density, in gravity at the surface, in the pressure and temperature of the interior would be extreme. This compression, this near constant size across a wide range of masses, is one of the quieter astonishments of brown dwarf physics. It is not an approximation or a simplification. It is a consequence of quantum mechanics operating at scales and pressures that have no terrestrial equivalent, producing an effect that reshapes the relationship between mass and size in ways that ordinary intuition simply cannot prepare for. The first person to reason carefully toward the existence of these objects was Shiv Kumar, an Indian-American astrophysicist working in the early 1960s. At that time, the lower end of the stellar mass range was poorly understood. Stars were known to grow dimmer and cooler as their mass decreased, following a smooth progression towards smaller and fainter objects. The question Kumar asked was not dramatic or unusual. It was a careful extension of existing physics. What happens, he asked, when the mass of a forming object drops below the threshold needed for sustained hydrogen fusion? What forms in that case, and how does it behave? Working through the physics of gravitational collapse and nuclear ignition, Kumar concluded that the answer was something forms. An object below the hydrogen burning threshold does not simply disappear. It collapses from its cloud of gas and dust as any stellar object does. It heats through gravitational compression, and it arrives at a configuration that is stable, supported against further collapse by quantum degeneracy pressure, but unable to sustain the nuclear fire that would have made it a star. He described these objects in a 1963 paper, and he called them, at that time, black dwarfs, not for their color but for their faintness, the dim endpoint of a failed stellar formation. The prediction was precise and physically grounded. Kumar laid out the mass thresholds, the pressure conditions, the quantum mechanical support mechanism. He described what these objects should be like in their interiors. He estimated their temperatures and luminosities. He placed them clearly in the theoretical landscape of stellar physics. And then, for more than 3 decades, no one could find them. This was not for lack of interest. The problem was observational. A brown dwarf, as Kumar had described it, would be faint, extremely faint, and cool. Its light, such as it was, would emerge primarily at infrared wavelengths, in the part of the spectrum beyond red, where the human eye is blind, and where the instrumentation of mid-20th century astronomy was limited. Infrared detectors capable of the sensitivity required did not yet exist, and because brown dwarfs have no fixed, stable luminosity, they cool continuously, growing dimmer over billions of years. There was no obvious characteristic brightness to search for. They could be almost anywhere in temperature space, depending on their age. An old brown dwarf might be so cool and dim that even a well-designed search could overlook it. A young one might be warm enough to be mistaken for something else. Kumar's theoretical brown dwarfs sat in the astronomical literature as a well-reasoned prediction, confirmed by the physics, uncertain in the observations, waiting. The name changed in 1975. Jill Tarter, an astronomer, then working on her doctoral research, found herself needing a term for these objects, the objects Kumar had predicted, the objects that had no confirmed examples, but occupied a clearly defined physical space. Black dwarf was already a term used for something else, the cold remnant of a white dwarf star that had exhausted its remaining heat after billions of years. And the color, if brown dwarfs emitted primarily at infrared and red wavelengths, in the dim range where these objects were expected to glow, was not truly black. It was dark, yes, but with a residual warmth. Something between a full stellar glow and the absence of light altogether. Tarter settled on brown dwarf. The name was not literal. Brown dwarfs do not appear brown in any ordinary photographic sense. Their light, if made visible to human eyes, might appear as a deep dark red, a dim coal glow, the color of an ember far from the fire. But brown dwarf captured something important. Not the bright blue or white or yellow of a true star, not the invisible cold of a planet past all nuclear warmth, but something intermediate, something warm without being luminous, something old and cooling. The name also acknowledged their compact size, dwarf, placed alongside terms like white dwarf and red dwarf, locating these objects in the family of small, dim, dense celestial bodies rather than among the giants. The term moved into the scientific literature and stayed. It named something that could not yet be seen. There is a particular quality to this kind of naming, assigning a word to an object confirmed by physics and predicted by careful reasoning, but not yet found by a telescope. The mathematics said these objects existed. The physics said they must form, given how stars form, given that the process of gravitational collapse operates across a range of masses and does not stop precisely at the hydrogen burning threshold. The logic was clean and the prediction was specific, and yet the actual objects, the specific glowing masses in the specific dark patches of specific parts of the sky, remained theoretical. Brown dwarfs, named in 1975 and predicted in 1963, would not be confirmed until 1995. That gap, 32 years from Kumar's paper to the first confirmed detections, is not a period of uncertainty about whether they existed. The physics was never seriously in doubt. The gap was technological. The instruments did not yet exist that could find them. But the objects themselves were never waiting. They were forming all along, in the cold molecular clouds where stars form, in the same processes, from the same materials. They were collapsing, heating, briefly fusing their trace quantities of deuterium, cooling. The brown dwarfs that were eventually found in 1995 were not young objects newly made. Many of them were ancient, already billions of years old, already far along in their long cooling descent. They had been present in the sky for as long as the stars around them. They simply had no name in the human record and no confirmed presence in the human catalog until the instruments and the methods and the searching finally caught up with what the physics had long insisted must be there. In the vastness of the galaxy, there may be as many brown dwarfs as there are stars. Some estimates suggest they are roughly as numerous. They drift through the same interstellar neighborhoods, occupy the same kinds of space, formed from the same kinds of clouds. Most of them float alone, unlit, undetected, cooling on their own long timescales through temperatures and spectral regimes that have taken decades of patient observation to begin to understand. The mass range they occupy, 13 to 80 times the mass of Jupiter, sounds precise, and in physical terms it is. These are real thresholds set by nuclear physics, not by observation or convention. But the objects within this range are enormously varied. A brown dwarf near the upper boundary, just below 80 Jupiter masses, is close enough to stellar ignition that it glows with a warmth approaching that of the coolest true stars, its surface temperatures reaching into the range of 2000 Kelvin. A brown dwarf near the lower boundary, just above 13 Jupiter masses, may be ancient and cold, its surface temperatures dropping below 500 Kelvin, its light emerging entirely in the mid-infrared, where only specialized instruments can detect it. Between these two extremes, within a single named category, lies an enormous range of physical states, and every brown dwarf within this range is moving, not through space, though they do move through space, but through temperature. Every one of them is cooling. Every one of them occupies, at any given moment, a position on a curve that began at formation and descends, without pause and without interruption, for as long as the object exists. This is one of the things that makes brown dwarfs genuinely unlike anything else. A star, once it reaches the main sequence, stabilizes. Its luminosity and surface temperature remain essentially constant for millions or billions of years, depending on its mass, until the hydrogen in its core is exhausted and it begins to change. The stability is the point. Stars are, in one sense, very long-lived steady states. A brown dwarf has no steady state. From the moment of its formation to the far end of its existence, it is always becoming something slightly cooler, slightly dimmer, slightly less than it was before. This is not a flaw in their nature. It is their nature. The cooling is not a failure mode or a degradation. It is simply what a brown dwarf does, as completely and continuously as a star burns. The difference is that burning holds things stable, while cooling carries an object gradually, inevitably, into deeper and deeper quiet. The mass boundary at 80 Jupiter masses, the upper limit, where a true star begins, is not perfectly sharp in practice. Near the hydrogen burning threshold, the ignition of sustained fusion is a gradual process rather than a sudden switch. Objects very close to this mass boundary may fuse small amounts of hydrogen for long periods without ever quite reaching the full self-sustaining proton-proton chain. The transition zone between the most massive brown dwarfs and the least massive true stars, the red dwarfs, the M-dwarf stars burning their hydrogen on timescales longer than the current age of the universe, is genuinely blurry when examined closely. But the physical principle holds. There is a temperature that must be reached and sustained in the core for hydrogen burning to become self-perpetuating, and brown dwarfs do not reach it. Their cores arrive at temperatures that are extraordinary by any familiar measure, millions of degrees, pressure enough to deform matter, and they stop there, held not by equilibrium, but by insufficiency. Not enough mass, not enough gravity, not enough compression. The proton-proton chain stays just out of reach, like a fire that needs one more degree of heat to catch and never receives it. Shiv Kumar's 1963 paper sat in the literature for years before the broader astronomical community had the tools to take it further. He had described the physics with care. He had drawn the mass boundaries. He had explained the quantum mechanical support mechanism. He had noted that these objects would be dim and infrared bright, and he had named them, if imprecisely, as a class of object distinct from both stars and planets. What he could not do in 1963 was find one, and in the absence of observed examples, the theoretical prediction remained what it was, correct but unconfirmed. It was a category waiting for its first members. The waiting itself has a kind of depth to it when considered carefully. The solar system has existed for 4.5 billion years. For most of that time, the brown dwarfs of the galaxy were cooling in the dark, indifferent to the absence of a name. They formed and glowed and cooled and continued to cool, and in the early 1960s, a physicist at a desk worked through the equations describing their physics with no instrument that could find them and no way to know how many there were, or where they were, or how their atmospheres behaved. He wrote down what physics required, and he was right, and then the universe waited for the instruments. By 1975, the term brown dwarf had been added to the language of astrophysics. The naming did not create the objects. The naming did not even help find them. That would require improvements in detector sensitivity, computational power, and observational strategy that would take another 20 years to arrive. The naming simply gave the category a word more precise than the blank space that had preceded it, a word that acknowledged, with a kind of quiet confidence, that these objects were real, that they were out there, that the physics was solid, and that eventually the instrumentation would arrive. Jill Tarter chose the name for its color, or for the approximation of a color, the dim, warm glow at the edge of what is visible, the not quite red of an object radiating heat it cannot replenish. Brown dwarf was not a statement about what could be seen. It was a statement about what was known through physics, given a label appropriate to its character, placed in the sky, in theory, before it could be placed there in observation. The gap between the naming and the finding was not empty. In that gap, astronomers refined their understanding of what they were looking for, what signatures a brown dwarf would leave in various wavelengths of light, how to distinguish a brown dwarf from a very cool star or a very massive planet when the photons finally arrived. The naming had made the search specific. Brown dwarf was not an abstraction. It was a description of physical properties, a certain mass range, a certain temperature range, a certain kind of spectral character that could be searched for even before any example had been found. In the dark of interstellar space, across the 32 years between Kumar's paper and the first confirmed detections, the brown dwarfs continued to drift and cool. They did not know they were theoretical. They did not know they were unnamed. They occupied their mass range with the same indifference that the stars occupy theirs, and they cooled, and their surfaces settled through temperature regimes that no astronomer had yet named or catalogued. And the faint infrared warmth they radiated moved outward through space at the speed of light, carrying the signatures of their chemistry and their temperature, waiting for a detector sensitive enough to collect it. The concept of a threshold is worth staying with for a moment. The hydrogen burning threshold at 10 million Kelvin is not a suggestion. It is not a typical value or an average condition. It is a physical requirement written into the behavior of protons at extreme temperatures and pressures. Below that temperature, the rate of proton-proton fusion events per unit volume, per unit time, is too low to sustain the star against gravitational collapse. Above that temperature, the rate is sufficient. The threshold is narrow. A core temperature of 9 million Kelvin is not close enough. A core temperature of 9.5 million Kelvin is not close enough. The process that would have made these objects into stars required the full 10 million, required more precisely the pressure conditions in the core that correspond to the mass of hydrogen and helium above, which is to say, it required enough mass. Without that mass, the temperature cannot be reached, and without the temperature, the fire cannot catch. This is the defining fact of a brown dwarf's existence, and it is a fact established once, at formation, and never revisited. Your toy here, a brown dwarf, does not gradually approach the hydrogen-burning threshold as it ages. It moves away from it, cooling, settling into lower temperatures over billions of years. The window in which it could, hypothetically, have been a star, the brief early phase of maximum compression and maximum core temperature, closes within the first few million years of the object's life. After that, the core temperature only falls. The threshold recedes into the past, a possibility that the physics foreclosed before the object was old enough, in any meaningful sense, to be described as old. This is not a tragedy in any human sense. The category has no regret built into it. Brown dwarfs do not fail in the way that implies an attempt. The mass was set at formation, the physics followed from the mass, and the object that resulted is exactly what its physics required it to be, something warm and dense and slowly cooling, occupying the space between stars and planets with a physical precision that has taken decades of observation and calculation to fully describe. The lower threshold, at 13 Jupiter masses, is in some ways equally interesting. Above it, the brief deuterium fusion occurs, a few million years of modest nuclear warmth, small by stellar standards but real. Below it, the object has no nuclear burning of any kind. The threshold does not change the long-term fate. Whether or not a brown dwarf burned deuterium in its early life, it is still cooling. The deuterium burning does not halt the cooling. It slows it slightly, briefly, and then it is over. But the threshold matters as a classification boundary, as the line below which an object has never produced nuclear energy of any kind and above which it has. A brown dwarf, then, is defined by two thresholds it sits between: above 13 Jupiter masses, capable of some nuclear burning, however brief and limited; below 80 Jupiter masses, incapable of sustained hydrogen burning. Within that range, the whole class lives, dozens of times the mass of Jupiter, roughly Jupiter's size, nuclear energy exhausted within a few million years of formation, left with only the slow outward radiation of warmth accumulated during collapse. And in that space between the thresholds, in the faint infrared glow of objects neither stellar nor planetary, an entire family of worlds exists that the solar system contains nothing like. They have atmospheres, complex, cloud-bearing, chemically active atmospheres, driven not by the light of a star, but by their own residual heat. They have interiors that span enormous pressure ranges from surface to core. They have magnetic fields and rotation rates, and in some cases companions, other brown dwarfs, planets or stars, whose gravity shapes their evolution. They cool through spectral regimes that shade from the warmth of dim stars to the cold of conditions no star ever reaches. They are, in their way, complete worlds. Shiv Kumar described them in 1963, before any had been found. He drew the boundaries of the category from first principles, from the behavior of nuclear physics at extreme temperatures and pressures, and he placed them in theoretical space with the confidence of careful reasoning rather than observation. What he predicted was real. The mass range was real. The temperature thresholds were real. The quantum mechanical support was real. The faint infrared warmth was real. And 12 years after he wrote the equations, before any telescope had found an example, Jill Tarter looked at that theoretical space, that gap between the smallest stars and the largest planets, that region where physics required something to exist, but observation had not yet confirmed it, and she gave it a name: brown dwarf. A name chosen for the quality of light a cooling failed star would emit if its light were shifted into visible wavelengths. Not the bright white or yellow or red of a true star, but something dimmer and darker and warmer than cold, something at the edge of what is visible, something between one thing and another. The name existed in the literature for 20 years before the objects were confirmed. In the time between the naming and the finding, the brown dwarfs of the galaxy continued to drift through the interstellar dark, cooling on their long trajectories, carrying in their interiors the quantum mechanical pressure that held them stable, radiating at wavelengths the instruments of the time could barely reach, named and waiting, present in theory, present in physics, present in the dark, in the faint warmth of infrared light, spreading outward into a universe that had not yet learned to read it. In the cold dark between the stars, far from any sun, a cloud of gas and dust hangs in near perfect stillness. It is not empty. The space between stellar systems is never truly empty. It is threaded with matter too thin and cold and spread to see, hydrogen and helium, and trace grains of silicate dust drifting without purpose or destination, through temperatures only a few degrees above the lowest possible. A cloud like this one stretches across light years. Its interior is darker than the dark around it, and denser and colder, and it has been gathering itself for longer than the Earth has existed. Somewhere inside the cloud, in a region no larger than a few times the distance between the sun and its nearest neighbor, The gas has grown slightly denser than the rest. Slightly is enough. The extra gravity of that small excess draws more gas inward, which adds more mass, which draws more gas still. The motion is almost imperceptible at first, not a collapse so much as a very slow leaning inward, the whole mass inclining toward a center that did not exist until the mass began to form it. There is no sound. There is no light. The cloud does not know what it is becoming. It is only falling. This is how nearly everything in the universe begins. A star begins this way. A brown dwarf begins this same way. From the outside, in these first millions of years, they are indistinguishable. Both are falling clouds, both warming slowly at their centers, both embedded in the same dark, dusty nurseries scattered through the arms of the galaxy. The difference between them is a difference of degree, not kind. One will fall inward until its core grows hot enough and dense enough to force hydrogen nuclei together against their own repulsion. The other will not. The other will fall only so far, and then stop, and then spend the rest of its existence cooling from the warmth of that falling. Before it can cool, it must form. The cold molecular clouds where brown dwarfs are born are among the largest structures in the galaxy that can be called a single thing. They span tens of light years. They contain the mass of thousands or hundreds of thousands of suns, spread so thin that the density in the densest parts is still far lower than the best vacuum achievable in a laboratory on Earth. What makes them cold is precisely what makes them dark. They contain no internal energy source, no fusion, no radiation of any kind, and so they cool by radiating their own faint infrared warmth out into a universe colder than they are. Carbon monoxide and other molecules rotate and vibrate and emit photons, and each emitted photon carries a little energy away, and the cloud grows colder still, and colder clouds are more susceptible to gravity, and so the cooling feeds the collapse, just as the collapse feeds the cooling. Over millions of years, small variations in density grow until the densest regions cross a threshold, the point where gravity becomes stronger than the outward thermal pressure that resisted it, and a clump begins to fall. The clump that will become a brown dwarf is not a small clump. It might contain 10 or 20 or 60 times the mass of Jupiter. As it falls, it compresses, and compressed gas grows warm. The center grows warm first, then warmer, then hot, hot in a way that has no earthly comparison, where thousands of Kelvin at the core still represents only the beginning of a temperature range that a true star would have to multiply 100-fold to reach. The heat builds pressure, and the pressure resists the continued infall, and the object enters a long, uncomfortable equilibrium, gravity pressing in, thermal pressure pushing out, the two forces neither perfectly balanced nor decisively resolved. This phase is called the Kelvin-Helmholtz phase, named for the mechanism that drives it, the slow conversion of gravitational potential energy into heat as the object shrinks. It is not nuclear burning. It requires no fusion at all. It is simply the warmth of falling, the heat generated whenever a massive object contracts under its own weight. During the Kelvin-Helmholtz phase, a young brown dwarf glows. It glows more brightly during this period than it will at any other point in its existence. The surface temperature of a very young brown dwarf can be several thousand Kelvin, far lower than the surface of the sun, but warm enough to produce a visible reddish-orange glow at infrared wavelengths, and in the brightest cases, a faint visible light as well. A brown dwarf in this early phase, embedded in the dusty disk of material still swirling around it, might be difficult to distinguish from a young low-mass star at the same age. Both are contracting, both are glowing with the heat of contraction. Both are embedded in similar environments. The difference that will separate them later, whether the core temperature eventually reaches the threshold for sustained hydrogen fusion, has not yet revealed itself. This is a strange kind of birth. The object is genuinely luminous in its infancy, genuinely radiating heat into the surrounding space, genuinely warming the material in its vicinity. The dust in its surrounding disk absorbs its radiation and re-emits it at longer wavelengths, producing the complex infrared signature that astronomers use to identify young stellar and substellar objects. To the surrounding cloud, the newly formed brown dwarf is a warm point in the cold, and the cloud does not know or care that this warmth will not last, that unlike the warmth of a true star, it has no fuel behind it and will fade on a time scale of millions of years rather than billions. Within the core of a very young brown dwarf, if its mass exceeds roughly 13 times the mass of Jupiter, there is a brief nuclear episode. At core temperatures of around 1 million Kelvin, deuterium, a heavy form of hydrogen, whose nucleus contains one proton and one neutron rather than just a proton, will fuse. Deuterium fusion does not require the enormous temperatures of ordinary hydrogen fusion. It ignites at a threshold far below the 10 million Kelvin needed to drive the proton-proton chain. In a brown dwarf massive enough to reach that lower threshold, deuterium burning provides a short pulse of nuclear energy, genuine fusion of genuine nuclei, releasing real energy that supports the core against a little more contraction. The brown dwarf, for a few million years, is not completely unlike a very small star. But the deuterium runs out. It was never abundant. Deuterium makes up only a tiny fraction of the hydrogen available, and a few million years is a brief time in the context of an object that will continue to exist for hundreds of billions of years. When the deuterium is gone, the core loses its nuclear heat source, and the balance of forces shifts. Gravity presses inward without the extra support. The core contracts a little more, heats a little more, but never enough to ignite ordinary hydrogen, never enough to reach the 10 million Kelvin that would have made this something else entirely. The contraction slows and then nearly stops, held up at last not by heat, but by a different kind of pressure, quantum mechanical and independent of temperature, arising from the fundamental nature of electrons rather than from energy at all. The object has arrived at its adult form. It is not a star, it is a brown dwarf, and it has already passed the brightest moment of its life. Not all brown dwarfs arrive through the straightforward collapse of a molecular cloud fragment. The galaxy is full of young stars with disks, and those disks are not always stable. A protostellar disk, the flat rotating plane of gas and dust that surrounds a young star in its first few million years, contains most of the mass that did not fall directly onto the forming star. The inner regions of the disk are warm, heated by the young star at the center, and the material there tends to remain in small stable grains and gas molecules that orbit quietly and slowly build rocky planets over millions of years. The outer regions of the disk are cold. They are far from the central star, and the temperature drops steeply with distance. Cold gas is heavier than warm gas, in the sense that its thermal pressure is lower, and in the outer disk this means that the self-gravity of the disk material can become important. In certain conditions, when the disk is massive enough and cold enough and far enough from the stabilizing influence of the central star's tidal force, ripples of density form and grow. A dense ring develops a denser region. The denser region pulls more material toward it. The concentration deepens, curving the disk around it into a spiral arm that leads back to itself. If the condensation grows quickly enough, before the disk's own rotation can shear it apart, It can collapse into a distinct gravitationally bound object, a companion body, forming not through the slow accretion of grains, but through the rapid collapse of a large disk fragment. The masses that can form this way span a range that includes the brown dwarf regime, and objects formed through this pathway can remain in wide orbits around their parent stars, or can be nudged by subsequent gravitational interactions into elongated orbits or freed from the star gravity entirely. A brown dwarf formed from disk fragmentation carries the chemistry of that disk, enriched in carbon and oxygen and nitrogen in ratios that reflect the disk's distance from the star rather than the star's own composition, a slight chemical signature distinguishing this origin from the simpler molecular cloud pathway. Whether the distinction is always detectable is uncertain. The two populations, cloud-born and disk-born, may overlap in mass and in the kinds of orbits they occupy, and the evidence for separating them is not always clean. There is a third pathway, stranger and more violent than the other two. In the young star-forming regions of the galaxy, stellar nurseries are not quiet places. They are dense with newly forming objects, each drawing from the same reservoir of cloud material, each embedded in a swarm of other protostellar cores, all doing the same thing. In these crowded environments, gravitational interactions between young objects are common. A low-mass embryo, a core that has begun to collapse, and might, given time and undisturbed access to surrounding gas, grow into a brown dwarf, or perhaps even a low-mass star, can be deflected by the gravity of a more massive neighbor. If the deflection is strong enough, and the timing unlucky, the embryo is thrown outward, away from the dense cloud core where it was forming, out into the lower density regions of the cluster or beyond. Cut off from the gas reservoir that was feeding it, the ejected embryo stops growing. Whatever mass it has accumulated when it leaves the cloud core is the mass it will keep. If it has already gathered enough, 13 to 80 Jupiter masses, it leaves as a brown dwarf. If it has gathered less, it leaves as a planetary mass object. Either way, it drifts away from the cluster that made it, eventually escaping the loose gravitational hold of the stellar nursery entirely, becoming a free-floating object between the stars, with no star to orbit and no cloud to drift through. It carries only the warmth of contraction and the brief flame of its deuterium, which it will spend slowly over the next few million years before beginning its long, uninterrupted cooling. The evidence for ejection comes partly from the numbers. Young star-forming regions contain more brown dwarfs per star than would be expected if all brown dwarfs formed the same way as stars, and they contain significant populations of very low-mass objects that seem to lack the kinds of protostellar disks typical of objects that formed through undisturbed cloud collapse. Objects that were ejected before they could build substantial disks would look exactly like this, mass without the disk material that quieter formation produces. The picture is not settled, and more than one mechanism likely contributes to the population seen in any real cluster. The cloud collapse pathway, the disk fragmentation pathway, and the ejection pathway are probably all real and all active in different proportions in different environments. What they share is the outcome, an object in the brown dwarf mass range drifting through the galaxy, cooling, largely alone. In the first few million years after formation, a brown dwarf embedded in a star-forming region looks something like a cool, slightly underluminous young star. It might have a disk of its own if it formed through molecular cloud collapse with enough angular momentum to create one. That disk could contain enough mass to form moons, or small rocky companions, objects as large as Earth or larger, orbiting a substellar body in complete darkness, since the brown dwarf itself contributes no significant visible light, and there is no star in that system to provide any. Those hypothetical companions would be cold. If liquid water requires a specific temperature range, the distance from the brown dwarf at which liquid water might exist on a surface shifts inward as the brown dwarf cools, and it cools relentlessly. Any moon in a liquid water-friendly orbit around a young warm brown dwarf will find itself in a freezing orbit a billion years later. Nothing about brown dwarf systems promises stability of the kind that Earth takes for granted, but that is billions of years away. In the early million years, the nursery is still rich with material, and the brown dwarf is still warm, and the disk around it, if it has one, is still lit from above by the light of the more massive young stars nearby. The whole region glows with the emission of excited hydrogen and ionized gas and warm dust, and within that glow, the young brown dwarf is one warm point among many, not yet distinguishable by its nature, only by its relatively lower luminosity and cooler surface temperature compared to its true stellar neighbors. As the star-forming region disperses over tens of millions of years, as the winds of the most massive newly formed stars push away the remaining cloud material, and the cluster begins to drift apart, and the dense knot of young objects loosens into a looser association, the brown dwarfs drift with it. They cool as they drift. A brown dwarf born at the same time as the Sun, 4.5 billion years ago, has had the entire age of the solar system to cool, and over that time has descended from the relatively warm surface temperatures of its youth through a long, quiet sequence of lower and lower temperatures, growing dimmer at every visible wavelength, for its emission shifting further and further into the infrared and eventually into wavelengths that no human eye could perceive under any circumstances. The galaxy contains an enormous number of these cooling objects. The total population of brown dwarfs in the Milky Way is estimated, with considerable uncertainty, to be comparable to the number of stars, or perhaps somewhat lower. The estimates are difficult because older, colder brown dwarfs are close to invisible by any current method of observation, and the brown dwarfs easiest to detect are the youngest and warmest, and therefore the least representative of the population as a whole. The true number of objects in the brown dwarf mass range drifting through the galaxy is almost certainly much larger than what has been found, because most of them have cooled past the point where even sensitive infrared telescopes can reliably detect them at the distances where they would be expected to exist. Among all the places a brown dwarf might end up, the space close to a sun-like star is among the least likely. The orbital region within roughly 5 astronomical units of a solar-type star, a region in which the gravitational influence of the star is strong, and in which close companions might be expected to form and remain, turns out to be remarkably empty of brown dwarf mass objects. Stars are found there as stellar companions in binary and multiple systems. Planets are found there in large numbers around nearly every solar-type star surveyed at sufficient precision. But objects in the mass range between roughly 13 and 80 times the mass of Jupiter are conspicuously almost entirely absent from these close orbits. An astronomer named David Black gave this conspicuous absence a name in the early 1990s. He called it the brown dwarf desert. The desert is a statistical emptiness. It is real in the same way a measurement is real, not a single absent object, but an absence across hundreds of surveyed systems, a gap in the distribution of companion masses that is too wide and too consistent to be an observational artifact. Planet mass companions exist. Stellar companions exist. The intermediate range, which the physics of brown dwarfs occupies, is nearly empty. Among the closest and most carefully monitored sun-like stars in the galaxy, fewer than 1% have brown dwarf companions in close orbit. The comparable fractions for planetary companions and stellar companions are both significantly higher. Why the desert exists is not fully settled. Several explanations have been offered, and they may each carry partial truth. One is that the two formation mechanisms relevant to close companions, disk fragmentation for lower mass companions, and core capture or co-formation in the stellar molecular cloud, clump for stellar companions, each tend to produce objects outside the brown dwarf mass range at close separations. Disk fragmentation tends to form objects of planetary mass or lower, because the disk material available at close separations is usually insufficient to reach brown dwarf masses. Cloud fragmentation tends to produce objects that are stellar or near stellar in mass, because the gravitational dynamics of collapsing cloud fragments prefer mass ratios close to unity. The brown dwarf mass range falls in a gap between the two processes, neither massive enough to form through cloud co-collapse near a star, nor light enough to form through typical disk fragmentation. A second possibility is that brown dwarf mass objects do occasionally form in close orbits through disk processes or cloud fragmentation, but that subsequent dynamical evolution tends to remove them, either migrating them inward until the star swallows them or scattering them into wide orbits through interactions with other companions. The ejection mechanism that can produce free-floating brown dwarfs in star clusters might operate in scaled-down form in the vicinity of individual stars, displacing substellar companions before they can be detected. Both the formation gap and the removal hypothesis fit the observations approximately equally well, and distinguishing between them requires either a much larger survey sample or a much better theoretical understanding of what happens in young stellar systems during the first few million years after formation. What the desert says with certainty is that formation is not indifferent to mass. The universe does not produce objects of all masses with equal probability at all locations. The distribution is shaped by physics, by the scales at which different formation mechanisms operate, by the thermodynamics of gas and dust, by the tidal forces of central stars, and the gravitational chaos of crowded nurseries. The brown dwarf mass range arises wherever the right combination of conditions prevails, and those conditions are common in molecular clouds and in the outer regions of protostellar disks and in the dense chaos of young clusters, but rare in the quiet orbital space close to a middle-aged star. The desert holds a kind of silence that is different from ordinary emptiness. Ordinary empty space has nothing in it. The brown dwarf desert has a specific kind of nothing, a nothing shaped by the expectation that something should be there, calibrated against the populations on either side, measured against the presence of planets and stars that fill the adjacent mass ranges. It is an absence that tells a story about formation, about the different thresholds at which nature organizes mass into objects, about the difficulty of building something in a range that sits between the preferred outcomes of competing physical processes. The silence of the desert is not the silence of deep interstellar space, cold and uniform and unstructured. It is the silence of a question whose answer has not quite arrived, the particular quiet of a measurement that has been made carefully and returned nothing, and been made again. In the wider galaxy, outside the desert, brown dwarfs are everywhere in numbers that are difficult to imagine and impossible to directly count. They orbit stars in wide, cool arcs, too dim to have been found in older surveys, but within reach of sensitive infrared instruments. They drift alone through interstellar space, remnants of ejections from long dispersed nurseries, cooling through temperature ranges that correspond to different phases of their internal chemistry. The nearest known brown dwarfs to the solar system are at distances of a few light years, close by astronomical standards, close enough that their infrared signatures are detectable with modern instruments, and yet so dim that they went undetected for decades while their stellar neighbors were cataloged and named. A brown dwarf a few light years away and several billion years old has a surface temperature of perhaps 500 Kelvin or less. It emits almost nothing at the wavelengths of visible light. On the longest nights of winter, pointing a sensitive telescope at the right coordinates, its infrared glow resolves out of the noise as a faint, slightly reddish point of light against a field of much brighter stars. It is not moving fast. It drifts across the sky over the years at a rate measurable only by careful comparison of images taken years apart, a parallax and a proper motion that reveal its proximity and its isolation. There is no companion near it, or at least none yet found. It appears to have been alone for most of its existence, if existence is the right word, for a slow, uninterrupted thermal decay that began in a cloud that no longer exists and will end only in a cold so deep that no instrument currently imagined could detect it. A young brown dwarf and an old one are almost the same object separated by time. They have the same mass, the same radius, the same quantum mechanical interior. What changes is only the temperature, the surface warmth, the spectral character, the infrared color that encodes their age, as clearly as rings encode the age of a tree. The young one, still glowing with the heat of contraction and the last of its deuterium, is red and relatively bright. The old one, having spent billions of years radiating that heat away into the surrounding void, is dark and cold and nearly invisible. Both are the same failed ignition. Both are the outcome of a collapse that went far but not far enough, a warming that built towards something and then stopped, leaving behind an object that carries the warmth of its own formation as the only warmth it will ever have. Formation ends and cooling begins. The transition is not sharp. The object does not flicker off its early luminosity in an instant, does not cross some clear line from bright to dim. It simply dims, steadily and continuously, on a time scale so long that no human observation has ever watched a single brown dwarf move significantly along its cooling track. What is known is inferred from populations, from comparing objects of similar mass but different ages, using the known age of a stellar cluster to determine how old the brown dwarfs within it are, and then reading off their temperatures to trace the trajectory that each of them has followed. The trajectory is simple. It is a descent. It has no reversals, no plateaus, no periods of renewed warmth. The heat accumulated in the Kelvin-Helmholtz phase leaks outward continuously, carried by convection from the deep interior to the photosphere and radiated away as infrared light, and no new heat arrives to replace it. The interior cools, the surface cools. The spectral class shifts slowly from one temperature regime to another, the chemistry of the atmosphere changing as the temperature drops, new molecules becoming stable where others were previously too hot to persist. The object ages, and the aging is nothing more and nothing less than a cooling, quiet, steady, without drama, without conclusion, for a time so long it makes the current age of the universe seem brief. The brown dwarf that formed in the cold molecular cloud, that contracted and briefly fused its deuterium, and settled into its quantum mechanical equilibrium, drifts now through the galaxy carrying all of this history. The cloud that made it has dispersed. The cluster that surrounded it at birth has long since scattered into separate trajectories. The warmth at its surface is the last echo of the gravitational fall that built it, not the heat of fusion, not the heat of a star, but the residual warmth of a collapse that came close and stopped. In the outer reaches of the Milky Way, and near its center, and in the halo above and below the galactic plane, brown dwarfs drift in uncountable numbers through the old dark between the stars. They cool in silence. They have no companions, most of them, or they orbit parent stars at distances so wide and on timescales so long that the relationship between them is more like the relationship between two drifting pieces of debris than anything a human word for companion adequately describes. They carry in their interiors the compressed legacy of molecular clouds that formed billions of years ago, hydrogen and helium packed so tightly that quantum mechanics rather than temperature is what holds the structure open against further collapse. The brown dwarf desert remains empty around its solar-type stars, as it has been empty since those systems formed. The absence holds its shape. The gas that might have fed a brown dwarf in those close orbits went somewhere else into the star, into the planets, into the ejected remnants of the disk. No close brown dwarf companion formed, or if one did, it did not stay. The emptiness is stable and old and statistically robust. It is one of the cleaner gaps in the zoo of companion objects, a place in the mass distribution where formation physics fails to produce what might otherwise be expected, and the silence that fills it is as real and as measurable as any object it does not contain. Somewhere in the Milky Way, in a molecular cloud not too different from the one that began this account, a new clump of gas is crossing the threshold where gravity overtakes thermal pressure and the inward fall begins. The clump may have enough mass to become a star. It may not. The difference between the two outcomes is measured in a mass range, narrower than the difference between a large planet and a small star, and it will not be decided for millions of years when the core either reaches the temperatures required for sustained hydrogen fusion or falls short of them and begins its long, irreversible cooling instead. For now, the clump falls inward in near total darkness, the surrounding cloud radiating faintly in wavelengths no eye could see, the whole structure settling toward a center that is only just beginning to grow warm. The silence around it is immense and old. Whatever it becomes, it has already begun, deep inside a brown dwarf, far from any star, where no light from outside has ever reached, and no light from within has ever escaped anywhere that eyes could find it. The matter is packed so tightly that the ordinary rules of heat and pressure have given way to something older and quieter. The object is not burning. It is not exploding outward with the force of a sustained nuclear fire. And yet it is not collapsing either. Something holds it. Something pushes back against the immense weight of all that mass pressing inward from every direction, and that something is not warmth. It is a property of the electrons themselves, a constraint written into the deepest grammar of matter, and it would hold this object in its present shape even if every last trace of heat were somehow drained away into the surrounding dark. That pressure has a name. It arises because electrons, by the fundamental rules that govern their behavior, cannot occupy the same quantum state in the same place at the same time. When matter is compressed far enough, the electrons inside it run out of distinct states to occupy. They cannot be pushed any closer together without violating a principle so basic that the universe enforces it without exception at every scale, in every corner of space where matter exists. The resistance this creates does not depend on temperature. It does not weaken as the interior cools. The, it is structural, like the resistance of a wall to the hand that presses against it. And it is why a brown dwarf that has been cooling for 10 billion years still occupies almost exactly the same volume it did near the beginning. The compression has gone as far as it can go. The wall holds. This is the same mechanism that holds a white dwarf together after its star has burned through all its fuel and shed its outer layers into space. A white dwarf and the interior of a brown dwarf share this quality of quantum support, this refusal to collapse further, regardless of temperature. But where a white dwarf arrived at that state through billions of years of stellar burning, the brown dwarf was born into it. The compression happened during formation. The electrons were crowded into their packed configuration before any sustained nuclear fire ever began, and they have remained there ever since, indifferent to the slow cooling happening above them in the layers closer to the surface. One consequence of this quantum support is that brown dwarfs of very different masses end up with nearly the same physical size. An object containing 30 times the mass of Jupiter and an object containing 70 times the mass of Jupiter are both roughly the same diameter as Jupiter itself. The extra mass in the heavier object compresses the interior more, squeezing the same number of particles into a smaller volume, but the quantum pressure increases as the compression increases, and the two effects nearly cancel. With a result is a family of objects whose physical dimensions are almost uniform across a wide range of masses, so that looking at a brown dwarf from outside, the way a distant instrument might measure its apparent size, would tell almost nothing about how much mass it contains. The heaviness is hidden in the density, in the pressure, in the invisible quantum architecture of the interior. Hold that image for a moment. A sphere roughly the size of the largest planet in our solar system. Inside it, a density that has no comparison on any planet's surface. Hydrogen and helium pressed so hard that the electrons have been stripped from their easy quantum states and crowded together against the walls of a constraint they can never exceed. Hot still, and in a certain sense permanent. Not permanent in the way a star is permanent, fueled and self-sustaining, but permanent the way a stone is permanent, holding its shape because matter at this density simply has nowhere else to go. The interior does not sit still, though. That is the next thing to understand. The matter inside a brown dwarf is in motion, continuous and deep, and extending from somewhere close to the core all the way up through the outer layers to the base of the atmosphere. The motion is convection, the slow rising of warmer material and the slow sinking of cooler material, the same process that stirs a pot of water on a stove and drives the great circulation cells in a planet's atmosphere, but operating here across the full depth of the object through thousands of miles of dense compressed gas. Nothing inside a brown dwarf is still. Every part of it is, very slowly and continuously rolling, in a star like the sun. Convection is confined to the outer portion of the interior. Below a certain depth, the energy produced by fusion in the core is intense enough, and the opacity of the plasma is high enough that photons can carry the heat outward without the material needing to move. This region of outward traveling light is called a radiative zone, and it sits between the convective core and the convective outer envelope in many stars. It is a zone of relative stillness, not motionless, but calm compared to the tumbling currents above and below it. Energy there travels through the slow random walk of photons being absorbed and re-emitted billions of times as they work their way outward across hundreds of thousands of miles, a journey that may take 100,000 years in the sun. A brown dwarf has none of this. Without a sustained nuclear energy source at the center, the interior never develops the kind of steep, powerful outward energy flux that would allow photons alone to carry the heat. The temperature gradient is not steep enough to create a stable radiative zone. Instead, the whole interior remains unstable to convection. Warmer parcels of material are always lighter than their surroundings, always inclined to rise, always replaced by cooler material sinking in from above. The circulation reaches all the way down. The whole interior, from the deepest layers to the base of the cloud-forming atmosphere, is one continuous, slowly churning body of gas, and it has been churning in this way since the beginning. This deep, full convection has consequences that reach beyond the physics of heat transfer, because everything inside a brown dwarf is mixed together by the slow rolling of convective currents. Chemical species that form in one layer are carried throughout the object over time. Material from the deepest, hottest regions rises to the cooler upper layers, and material from the upper layers sinks back down toward the center. Nothing sits quietly in one place. The interior is, chemically and thermally, a single well-stirred body, with its contents gradually averaging out across the full depth. This is very different from a star with stable layers, where chemical composition can vary dramatically with depth, and where elements made in the core can remain sequestered there for billions of years. There is a particular element whose fate inside a brown dwarf makes this mixing matter in a way that reaches all the way out to astronomers observing from Earth. That element is lithium. In the early universe, and in the interstellar gas clouds that condense into new stars and brown dwarfs, lithium is present in small but measurable amounts. It is a lightweight element, fragile compared to most, with a nucleus that breaks apart at relatively modest temperatures, around 2.5 million Kelvin. In objects massive enough to reach those temperatures in their cores, the lithium is steadily destroyed. In a large enough star, the core burns hot enough to consume it, and in sufficiently massive and fully convective objects, the mixing carries all the lithium down into the hot interior where it is burned, eventually leaving the atmosphere depleted. A brown dwarf below a certain mass never reaches interior temperatures high enough to destroy its lithium. Its core stays too cool, and the lithium survives, mixed throughout the interior by convection, but never carried somewhere hot enough to break it apart. An object above approximately 65 times the mass of Jupiter, though, does reach temperatures sufficient to consume its lithium, and because the interior is fully convective, the consumption is total. The material is mixed down, burned, mixed back up as lighter products, and over time, the whole body is drained of its lithium supply. This creates a test. When the light from a brown dwarf is analyzed across its spectrum, the presence or absence of a specific absorption signature tells something important about the object's mass. Lithium absorbs light at a very specific wavelength, producing a dark band in the spectrum at 670.8 nanometers, a narrow notch in the light coming from the atmosphere, pressed there by the lithium atoms in the outer layers. If that band is present, the object almost certainly has not burned its lithium. It has not carried all of its interior material through a region hot enough to destroy it. It is almost certainly below that mass threshold of 65 Jupiter masses, and its substellar nature is written in that one quiet dark line. The test was proposed by Raphael Rebolo and his colleagues in the early 1990s. It gave observers a tool they had been looking for, a way to identify brown dwarfs not just by their temperature or luminosity, both of which can overlap with those of low-mass stars, but by a chemical signature specific to the internal physics of substellar objects. A low-mass star just above the fusion threshold and a brown dwarf just below it can look nearly identical from outside at similar ages. Both may be dim, reddish, small, but the lithium line, or its absence, carries a message from the interior that temperature and color cannot. It is a fingerprint pressed from the inside out. Hold the image of that dark spectral line for a moment. 670.8 nanometers. A very specific wavelength of red light, going slightly darker than the wavelengths on either side of it, in the spectrum of a faint and distant object. The lithium atoms in that atmosphere, mixed upward by convection from the depths, have absorbed that particular portion of the outgoing light, each one contributing an infinitesimal fraction of the dimming, all of them together creating a line dark enough to measure. That line is a record of what did not happen inside, a record of a temperature never reached, a record of a boundary approached but not crossed. The brown dwarf goes on cooling. This is in a sense the central fact of its existence after formation, the constant background of everything else. It began warmer, much warmer, in the early period when it was still contracting, and the gravitational potential energy of that contraction was being converted into heat. But once the contraction slowed, once the quantum pressure in the interior reached equilibrium with the weight of the overlying mass, that source of energy faded. The deuterium burned for a while, the heavy isotope of hydrogen fusing at temperatures around 1,000,000 Kelvin, producing a few million years of modest warmth. Then the deuterium was gone, burned through, the fuel too sparse, and the reactions too brief to leave much trace. After that, there was nothing left to sustain the temperature, no new energy flowing in, only the heat already stored in the interior, and the slow, inexorable leak of that heat outward through the atmosphere and into space. This cooling is not a catastrophic event. It does not happen quickly enough to observe within a human lifetime, or 1,000 lifetimes, or 1,000,000. It is a geological process operating on astronomical timescales. In the first few 100 million years, the cooling is fastest. The object is still comparatively warm, and the temperature gradient between the interior and the surrounding space is steep, driving a stronger outward flow of heat. Over billions of years, the temperature drops more slowly, the gradient shallowing, the flow of heat thinning to a trickle. The object grows cooler and cooler, losing energy at a rate that diminishes. As the energy remaining diminishes, the curve of its decline bending gradually toward the horizontal without ever quite reaching it. A brown dwarf born in the early universe, when the first stars and clouds were forming, has been cooling now for something close to 13 billion years. It began perhaps with an effective surface temperature of several thousand Kelvin, warm enough to glow a dim red in visible light, its spectrum dominated by the signatures of metal oxides and simple molecular species. Now, after all that time, it might have an effective temperature somewhere in the range of a few hundred Kelvin, less than the boiling point of water on Earth, less than the temperature of a planet's sunlit surface in the inner part of a solar system. Its warmth has been leaking into the cold of space for as long as the galaxy has been forming stars, and the object that remains is a kind of deep, slow memory of the warmer world it once was. It is worth holding the full time scale of that cooling in mind, not to perform how vast it is, but to let it settle into the listening body at the pace it deserves. 13 billion years. And while the light from some of these old brown dwarfs has been traveling toward us since before the sun existed, since before the molecular cloud that would eventually collapse into our solar system had begun its inward fall. The cooling happening inside them is not a quick process that we are catching at a particular moment. It is the condition of their existence, the one unchanging thing about them, that they are always, at every moment in their history, a little cooler than they were before. Not cold yet, perhaps, still warm in the deep interior, still glowing faintly in wavelengths the eye cannot see, but always without interruption, cooling. In the deep interior, the convective rolling continues while the surface temperature falls. Warmer material still rises from slightly deeper, still releases a little of its heat to the layers above, still sinks back down. The circulation is slower now than it once was. The temperature differences that drive it have grown smaller as the interior temperature has become more uniform, but it has not stopped. The currents move through the dense compressed gas with a patience that has no human analogy, carrying incremental amounts of heat outward in currents that may take centuries or longer to complete a single cycle. The interior is stirred slowly by physics that does not hurry, and the heat that rises to the surface and escapes into space represents a tiny fraction of what remains stored in the compressed mass below. What comes up through those convective currents meets, at the top of the interior, an atmosphere of increasing complexity. The exact character of that atmosphere depends on where the brown dwarf currently sits on its cooling curve, whether it is still comparatively warm or has descended through many billions of years toward the lower temperatures at the end of its long arc. The chemistry of the atmosphere shifts with temperature in ways that are systematic and identifiable from the outside, each temperature regime producing a different set of molecules, different clouds, different patterns of absorption in the outgoing infrared light. The atmosphere is, in this sense, a display of the interior's thermal state, a surface readout of the cooling that has been happening below for the entire lifetime of the object. But before the atmosphere, there is a boundary, a transition zone, between the deep interior and the layers where temperature and pressure have dropped far enough for chemistry to take over from raw thermal dissociation. In the deep interior, temperatures are too high for most molecules to exist. Hydrogen exists as individual atoms or as ions, the electrons stripped away. Moving outward through the interior, the temperature falls and molecular hydrogen forms from the atoms. The atmosphere above is cooler still, and progressively more complex molecules begin to appear. Water vapor, then carbon monoxide, then methane in the coolest brown dwarfs. This transition from atomic to molecular chemistry is continuous and gradual, following the smooth temperature gradient from the interior outward, and it is part of what makes the atmosphere such a sensitive record of the object's temperature. The lithium atoms in the atmosphere are mixed up from below. Their presence in the spectrum is the last clue from the interior, a message carried on convective currents from the depths and released into the outgoing light at the surface. When an astronomer on Earth detects that dark line at 670.8 nanometers, they are receiving a signal that began inside a body, perhaps the size of Jupiter, passed through thousands of miles of hot compressed gas, was carried upward through convective circulation, and finally absorbed one specific wavelength of the outgoing light before the rest of the spectrum completed its journey across light years of space to a waiting instrument. That signal carries the entire internal history of the object encoded in its presence. The quantum pressure does not care about any of this. The electrons in the interior continue to push back against the weight of the overlying mass, regardless of how much heat has escaped, regardless of what the surface temperature reads, regardless of whether the lithium line is present or absent in the spectrum. The object's size does not change measurably as it cools. A brown dwarf that was the size of Jupiter in its first million years is still the size of Jupiter now, and it will be the size of Jupiter when the universe is several times its current age. The quantum constraint that holds it together is not temporary. It does not weaken over time. It is the permanent architecture of the object, set in place during formation, unchanged by everything that has happened since. This permanence of size in the face of continuous cooling is one of the stranger qualities of brown dwarfs when held alongside the behavior of ordinary matter. A hot object ordinarily expands when heated and contracts when cooled. The thermal motion of its particles drives them apart or allows them to come closer together, depending on temperature. In a brown dwarf's interior, the quantum degeneracy pressure is so dominant that thermal pressure is almost negligible in comparison. Heating the interior slightly would not cause it to expand appreciably. Cooling it would not cause it to contract. The size is fixed not by temperature, but by mass and quantum mechanics, and the thermal state of the interior is almost irrelevant to its dimensions. Step back from the interior for a moment to hold the full picture. A sphere the size of the largest planet in the solar system, but containing perhaps 30 or 50 or 70 times as much mass. The interior compressed to densities that push electrons into their quantum limit. Convective currents rolling slowly through the full depth of the object, from something close to the center all the way to the base of the atmosphere, carrying heat upward on time scales measured in centuries per cycle. The lithium surviving in the outer layers if the interior never grew hot enough to destroy it, or gone if it did. The surface slowly cooling across billions of years, moving through temperature regimes that change its spectrum from warm and reddish to cooler and darker, while the interior holds its shape against gravity with the same quantum pressure it has always held. There is something almost restful about the interior of a brown dwarf at this scale. Not restful in the way of emptiness, but restful in the way of something settled, something that has found its equilibrium and will not be moved from it by the passage of time. The stars burn and explode and collapse. The planets are heated by their parent stars and cooled by the shadow of night and warmed again. But the interior of a brown dwarf sits in its quantum balance, mixed by slow currents, drained of heat, so gradually that the cooling is invisible across any time scale a human civilization could measure. It persists. It continues. It loses a little more of its warmth with every year that passes, and in that loss there is nothing dramatic, nothing catastrophic, only the steady thinning of the thermal energy stored in the compressed matter at the center of a world that never quite became a star. The full convection of the interior has one more consequence worth dwelling on before moving from the deep interior to the atmosphere above it. In a sun-like star, the stable radiative zone creates a kind of thermal buffer, a region where temperature changes slowly and where the composition of the gas at different depths can remain different from the composition at other depths for long periods. In a brown dwarf, the full convective mixing removes any such stratification. The interior tends toward a uniform composition at any given moment, with the same average mix of elements throughout. If a chemical reaction consumes a species in the hot depths, the convection replenishes those depths from above, while simultaneously distributing the products upward. The whole object acts as a single chemical reactor rather than a stack of distinct layers with different compositions and different reactions occurring at each. This uniformity matters for the lithium, and it matters for a few other elements and molecules whose presence or abundance in the atmosphere carries information about what has happened in the interior. The atmosphere of a brown dwarf is not a sealed layer sitting atop an isolated interior. It is the top of a continuous column of material that extends all the way to the center of the object. thoroughly mixed by billions of years of convective circulation. What reaches the surface reflects, in some measure, the history of the whole interior. The atmosphere is the readable face of a deeply interior process, and the spectrum of that atmosphere is the text of that face. The slow fall of temperature continues. At any given moment, the brown dwarf surface temperature is a snapshot of a position along a curve that will continue falling for as long as the object exists. There is no stable endpoint to aim for, no equilibrium that will be reached and then maintained the way a star maintains its luminosity through sustained fusion. The curve continues downward, decade by decade, millennium by millennium, era by era. The convection continues. The quantum pressure continues. The slow loss of heat continues. And in the quantum architecture of the interior, nothing changes at all. The electrons remain crowded into their limit, indifferent to the temperature above them, holding the object at the size it has always been, patient in the way that physics is patient, which is to say, without thought or intention or effort of any kind. The cooling curve of a brown dwarf, if drawn across billions of years, is a smooth and continuous descent. It does not have the flat plateau of a star's main sequence lifetime, where luminosity is nearly constant, because fusion keeps replenishing the energy lost to radiation. It does not have the sharp decline of a supernova or the sudden drop of a rapid collapse. It is simply a long, gradual fall from warm to cool, from cool to cold, from dim to dimmer, without interruption or inflection, following the same mathematics of heat loss that governs a cooling stone or a cooling coal, only extended across timescales so long that the cooling rate at any single moment is effectively invisible. The rate of change is real, it is happening, but it is happening so slowly that the object appears at any moment in its history that an observer might happen to look to be completely unchanging. In the atmosphere, a little way above the top of the convective interior, the temperature has fallen to a level where chemistry becomes the dominant story. Not the quantum mechanics of compressed electrons, not the large-scale rolling of convective currents, but the assembling and disassembling of molecules from atoms, the condensing of mineral particles from hot gas, the formation and dissolution of cloud layers at different pressure levels in the atmosphere. The interior has handed off its heat to the atmosphere, and the atmosphere has its own complex response to that heat. But that response belongs to the outer layers of the object, to the weather and the clouds, and the spectral chemistry that makes each temperature regime look different from outside. The interior remains below, doing its quiet work. The quantum pressure holds, the convection rolls, the heat leaks outward through the atmosphere by fractions. On the lithium in the outer layers, if it is there, catches its specific wavelength of outgoing light and sends that dark line into space, a signal of what happened inside, or rather of what did not happen. The temperature never reached the threshold. The lithium was never carried into a region hot enough to destroy it. The threshold was approached and not crossed, and the evidence of that boundary is written in the spectrum in a single quiet absorption line, dark at 670.8 nanometers, present in the light of a world that has been cooling since long before the Earth was formed. Somewhere inside that object, the electrons are still stacked in their quantum states, still filling every available configuration, still pressing back against the weight of everything above them. The pressure is not generated by temperature. It is not generated by fusion. It is generated by the fundamental impossibility of matter being more than matter, of electrons sharing what cannot be shared, of compression going further than the rules of the universe allow. That pressure has been there since the object formed. It was there when the brown dwarf was young and warm and glowing with the infrared heat of gravitational contraction. It was there when the deuterium was burning and the object was brighter than it would ever be again. It is there now, in the long, slow middle of the cooling arc, the temperature falling across billions of years, while the quantum architecture beneath holds the size constant and the convective currents stir the contents from center to surface in slow, unending motion. It will be there still, undiminished, in 10 billion years, when the temperature at the surface has fallen further still, when the atmosphere has grown darker and colder, and the spectral signatures of the warm reddish cloud layers have long since given way to the chemical signatures of a much cooler world. The quantum pressure does not age, it does not diminish, it does not need to be replenished. It is a property of the electrons, and the electrons are not going anywhere. The object will hold its shape while it cools. It will hold its shape when it is too cold to detect in anything but the longest infrared wavelengths. It will hold its shape when the last traces of atmospheric warmth have diffused so far into the surrounding space that no instrument could measure them. The wall holds and will go on holding, in the dark, in the silence, in the patient quantum architecture of matter at the limit of its compression, cooling, always a little, from now until long after any star that ever burned near it has itself grown cold. In the high atmosphere of a brown dwarf, at a pressure just a few times thicker than the air above a mountain on Earth, there are clouds made of iron, not the rust-red dust of iron oxide, not anything the sky of Earth has ever held. These are droplets of liquid iron, suspended in a hydrogen atmosphere heated past 1300 Kelvin, drifting in slow dark layers through air that glows in no color the eye could receive. The clouds are dense and gray at their cores and trail thinner at their edges, and they move not because a star drives them, but because the world beneath them is stirring from within, churning with heat that has nowhere to go but slowly upward and then slowly out. There is no sunrise here. There is no day. The light that faintly reaches the outer atmosphere of this world comes only from itself, from the long thermal memory of the heat packed into it at its birth, bleeding outward through layers of iron cloud and silicate haze in wavelengths far below what human eyes were made to catch. From any great distance, the sky of this place would look black, the iron clouds would be invisible. Only an instrument tuned to the infrared would see them at all, and then only as a slight shifting in the way the world's warmth reaches outward, a pattern of variation, a rhythm, a slow turning of cloud against cloud in a sky that has never once been lit from outside. The iron droplets form because the temperature is exactly right for them to form. At the pressures and temperatures present in the upper layers of a brown dwarf hotter than roughly 1400 Kelvin, iron exists as a vapor mixed into the surrounding gas. Then, as the gas cools slightly with altitude, the iron condenses. It gathers into droplets the way water gathers from cooling air on Earth, but at temperatures that would incinerate any terrestrial surface. These droplets are not static. They are small enough to be carried by the slow motion of the gas, large enough to eventually sink back down through the atmosphere as they grow heavier. The atmosphere is never quite still. Somewhere in the cloud layer, iron is always rising as vapor, condensing, drifting, sinking. The cycle runs without a sun to power it and without a season to mark it. Alongside the iron, there are silicate particles. Magnesium silicates condense from the gas at similar temperatures, forming solid grains, fine mineral dust floating in the hydrogen air, opaque to the dim infrared light working its way up from below. In some layers, these silicate clouds are thick enough to obscure the deeper atmosphere entirely. The whole sky, from inside, would be a featureless mineral overcast with no horizon to speak of, just a deepening of haze in every direction until the opacity grew complete. Lower down beyond the silicate layer, the temperature rises quickly with depth. The chemistry changes. Heavier compounds remain in the gas phase. The pressure increases until it exceeds anything on Earth's surface by many times. And still the atmosphere has not reached what could be called the ground, because there may be no solid ground at all, only a gradual thickening of fluid into something denser, continuous with the atmosphere above it. The transition marked by pressure alone. It is quiet here in a way that has no earthly name, not the quiet of a windless night or a sealed room, something older than that. The iron clouds move. Their motion is driven by convection, the same large-scale rolling of material that operates inside the brown dwarf, all the way from its core outward through its atmosphere, with no division between interior and surface, one continuous churning. Where the convective currents are stronger, the clouds are thicker and more turbulent. Where they are weaker, the cloud layer is thinner, more patchy, and in some places almost absent. Gaps in the overcast through which the warmer, deeper layers below can radiate their heat more directly outward. These gaps are not fixed. They drift and close and reopen over days as the brown dwarf turns. A brown dwarf rotates. Most rotate quickly, faster than Jupiter, completing a full turn in somewhere between 2 and 12 hours, driven by the angular momentum they gathered when the gas cloud that made them collapsed inward. And as the world turns, its cloud pattern turns with it. A region of thick iron overcast rotates into the line of sight. A thinner patch follows it. Then the thick region returns, watched from the distance of a telescope, an infrared telescope, sensitive enough to catch the warmth of an object, 1400 Kelvin, and no brighter. This rotation produces a subtle breathing in the light. When the thick clouded region faces outward, the warmth from below is blocked, and the brown dwarf appears slightly fainter. When the thinner patch faces outward, more warmth escapes, and the brown dwarf is slightly brighter. The variation is small, a few percent at most, a rise and fall no eye could see directly, but that a careful measurement over several hours lays out as a gentle wave. The period of that wave is the rotation period. The shape of that wave carries information about how the clouds are distributed, how wide and deep the thick patches are, whether there are multiple distinct regions or a more complex and asymmetric pattern. The clouds themselves are not stable over long periods. They form and dissipate and reform in configurations that differ from one rotation to the next, so that the light curve measured over one night may differ measurably from the curve measured a week later. This is not unusual behavior. It is the ordinary behavior of a dynamic atmosphere, the kind of variation seen on Jupiter and Saturn, where the cloud bands shift over years and storm systems appear and vanish, and the great red spot has been present for centuries, but was not always the same. On a brown dwarf, the same physics plays out without a solar wind to drive it, without a magnetic coupling to a central star, in iron and silicate rather than water and ammonia ice. The planet-like and the star-like are mixed here in a way that fits neither category comfortably. The atmosphere is planetary in its composition and its behavior, but the energy driving it comes not from a star overhead, but from the world's own deep interior, radiating heat it has carried since its formation. This is weather driven by memory. The heat that stirs these iron clouds was gathered billions of years ago in the collapse of a gas cloud, converted from gravitational potential into thermal energy as the object contracted, and it has been bleeding outward ever since. The iron clouds are the visible record of that process, the outermost edge of a slow thermal exhale that has been running since before the Earth existed. A cooler brown dwarf is a different world. When a brown dwarf ages past the point where its effective surface temperature drops below 1400 Kelvin, something shifts in the atmosphere. The iron and silicate clouds, which were suspended in the upper layers by the turbulent gas at higher temperatures, begin to sink. As the photosphere cools, the equilibrium point at which iron can condense drops lower and lower in pressure, further down into the atmosphere, below the layer from which most of the outgoing radiation escapes. The upper atmosphere, once thick with mineral haze, begins to clear. This clearing happens over millions of years, too slowly to watch in any individual case, but its result is unmistakable when a cooler brown dwarf is compared to a warmer one. The upper atmosphere of a brown dwarf below roughly 1400 Kelvin is not gray and cloud-laden. It is relatively transparent, and through that transparency, a different chemistry becomes visible. Methane, which forms from carbon and hydrogen at lower temperatures, begins to appear in significant quantities. At warmer temperatures, the carbon in the atmosphere tends to be locked into carbon monoxide, which does not absorb infrared light in the same characteristic way. Below about 1400 Kelvin, the balance shifts. Carbon monoxide becomes less stable. Carbon and hydrogen combine instead into methane, a molecule with deep and distinctive absorption features at specific infrared wavelengths, particularly at 1.6 and 2.2 microns, where it absorbs outgoing radiation strongly enough to leave clear marks on the spectrum. The appearance of methane changes everything about how a brown dwarf looks to an infrared instrument. The spectrum, which in a warmer object was shaped primarily by water vapor, carbon monoxide, and the broad reddening influence of mineral cloud opacity, now carries the methane signature like a new voice entering a room, specific, legible, unmistakable. Water vapor is still present, still absorbing at its own wavelengths. But methane adds to it a new pattern, a new set of bands where the outgoing warmth is absorbed and withheld, shaping the infrared light into something that carries a chemical record of the world's temperature. Something happens to the color as well. A warmer brown dwarf, seen in infrared, is relatively red, meaning it is brighter at longer infrared wavelengths than at shorter ones, partly because of the silicate and iron cloud opacity that scatters and absorbs shorter wavelengths preferentially. When the clouds sink out of the observable atmosphere and the upper layers clear, the color shifts. The cooler brown dwarf becomes bluer in the infrared, not because it is hotter, but because the cloud opacity is gone, and the methane and water absorb the longer wavelengths more strongly than the shorter ones. The color shift is in the opposite direction from what temperature alone would predict. It is a sign not of warming, but of clearing, a transparency that paradoxically makes the light look bluer as the world grows cooler and older. This transition, the clearing of mineral clouds, the emergence of methane, the color reversal, happens over a fairly narrow range of temperatures, somewhere between roughly 1200 and 1400 Kelvin, and it does not happen uniformly across all brown dwarfs at exactly the same point. Some begin to clear their clouds at slightly higher temperatures than others. Some show a patchwork transition, with regions that have cleared sitting alongside regions that are still thick with haze, producing a particularly complex and variable infrared signal. The narrow temperature window over which this shift occurs means that there is a striking diversity of appearance among brown dwarfs at nearly identical temperatures, some looking redder, some bluer, some highly variable, and some almost steady, all crossing the same threshold at slightly different moments in ways that probably reflect real differences in their atmospheric physics. It is one of the livelier questions in the study of these objects, why some cross the threshold cleanly and others linger in an intermediate state, half cleared, half hazy, for longer than the models predict. The deep interior below all of this is still moving. The convective circulation that carries heat from the core outward does not stop at the atmosphere's lower boundary. It enters the atmosphere and continues, and in some brown dwarfs, the convection is vigorous enough to reach even into the cloud layers, disrupting them from below and producing the patchy dynamic cloud distributions that the infrared light curves record. The convection also carries chemical species upward from deeper, hotter layers and down from cooler ones, mixing the atmosphere in ways that can produce abundances slightly different from what chemical equilibrium alone would predict. Carbon monoxide, for instance, which is stable at depth but not in the upper atmosphere, can be carried upward by convective currents faster than it has time to react and convert to methane, so that a slightly warmer atmosphere is detectable above where it should chemically survive. The atmosphere is not in perfect equilibrium. It is being stirred continuously by a world that is still, very slowly, cooling from within. In the deepest layers of the atmosphere that can still be observed, the layers from which light can still escape before being absorbed, the temperature is around 1,000 Kelvin. Below that, the temperature increases rapidly with depth. A few pressure scale heights lower, the temperature might be 3,000 Kelvin or more, easily hot enough for the iron and silicate to return to their vapor phase and enter the gas again. This is where the iron cloud layer sits in a cooler brown dwarf, not in the observable upper atmosphere, but far below it, still present, still condensing and evaporating in the slow convective cycle, but hidden behind the overhead column of gas, inaccessible to direct observation. The observable atmosphere is only the outermost layer of the story. Most of what is happening in a brown dwarf is happening in the dark behind that layer, in regions too deep for any photon to escape from, in pressures and temperatures that can only be inferred from the light that eventually does escape, shaped by everything it passed through on its way out. In an even cooler brown dwarf, one that has been cooling for billions of years, the methane signature deepens, water vapor absorbs more. The outgoing radiation shifts further and further toward longer infrared wavelengths, away from the near-infrared where most ground-based telescopes work best, and toward the mid-infrared where the technology required to detect it is more demanding and the sky above Earth is less cooperative. The effective surface temperature drops through 1,000 Kelvin, then through 800, then through 600. Below 500 Kelvin, a new molecule begins to appear in the spectrum, ammonia, which forms at low temperatures from nitrogen and hydrogen, has absorption features in the near-infrared. In warm brown dwarfs, the nitrogen in the atmosphere tends to form molecular nitrogen gas, which does not absorb in the same way. But as temperatures drop below 500 Kelvin, the balance of nitrogen chemistry shifts and ammonia begins to appear. Like methane before it, ammonia leaves a distinctive mark on the spectrum, a chemical signature that has cooled into existence over billions of years of gradual thermal descent. Its appearance marks a new regime of atmospheric chemistry, one that is colder than any planetary atmosphere in the solar system other than the outer gas giants. The sky of such a world is almost completely dark. The effective surface temperature is 500 Kelvin or less, comparable to the temperature of an oven set very high, warm enough that the object still radiates significant heat in the mid-infrared, but cold enough that in visible light, the world is essentially invisible. No red glow, no faint ember, just the slow outpouring of heat in wavelengths no eye would register, rising from a cloud layer made of substances no terrestrial atmosphere has ever contained, in a sky that has been dark for longer than any mountain on Earth has existed. Some of these cold brown dwarfs may have water clouds. At temperatures below roughly 350 Kelvin, and at the right atmospheric pressures, water can condense from the gas phase into ice crystals, forming a cloud layer analogous in chemistry to the water clouds of Earth, but embedded in a hydrogen-dominated atmosphere at pressures and temperatures that bear no resemblance to anything terrestrial. Whether any known brown dwarf has definitely reached the temperature regime where water cloud formation is possible is still an open question, sitting at the edge of what current instruments can resolve. The coldest known brown dwarfs are close to that threshold. Their atmospheres may already be hosting the earliest stages of water cloud formation in chemistry that remains too faint and too cold and too far away to confirm. What can be confirmed is the variation. Even among cold brown dwarfs, the infrared light curves show that their atmospheres are not uniform. The same slow rotation that produces variability in the iron cloud layers of warmer objects produces variability in the ammonia-rich, methane-dominated layers of colder ones, thicker and thinner patches, regions of slightly different chemistry or temperature, rotating in and out of view as the world turns through its 2 to 12-hour day. The rotation is one of the few ways the passage of time can be felt on one of these objects from the outside. There are no seasons because there is no star. There is no tide, in most cases, because there is no large nearby body to pull at the atmosphere. The only clock that runs on a brown dwarf's surface is its own spin, the regular return of each region of cloud to the same orientation relative to a distant observer, marking out a cycle that has no name in any human system of timekeeping, but that repeats steadily, hour after hour, year after year, for billions of years. The rotation may slow over very long periods, as internal dynamics redistribute angular momentum, but even this is slow, billions of years to make a detectable difference in the period. For most of its life, a brown dwarf rotates at essentially the same rate it was born with. The rhythm is ancient. The cloud pattern within that rhythm is not. It changes on the time scale of days and weeks and years, a complex and dynamic embroidery on an extremely stable frame. Below the cloud layers, below the convective atmosphere, below the point where chemistry still holds meaning, the interior of the brown dwarf is a dense, hot fluid of hydrogen and helium that is no longer quite a gas in the ordinary sense. The pressure there is high enough that the electrons and nuclei of the hydrogen atoms have been pressed together into a state where quantum mechanical effects dominate. It is warm, far warmer than the photosphere, but it is cooling, slowly, inexorably, on a time scale that makes geological time look brief. The heat at depth today is less than the heat at depth a billion years ago, and the heat at depth a billion years from now will be less than it is today. The cooling never stops. There is nothing to stop it. The atmospheric chemistry at the surface responds to this cooling in the same steady way. A brown dwarf that is currently producing a methane-dominated infrared spectrum will, given enough time, produce an ammonia-rich one. Then, in the extreme cold of what would be a very old and very faint object, it will become cooler still. Each stage of the cooling is chemically distinct, atmospherically distinct, spectrally distinct. The atmosphere at any moment in a brown dwarf's life is a record of how old it is and how much heat it was born with, written in the molecular species that have had time to condense and the ones that have not yet done so. There is something orderly in this, and something vast. The same laws that govern the condensation of morning dew on a blade of grass govern the condensation of iron droplets in the sky of a brown dwarf. The same relationship between temperature, pressure, and the chemical stability of compounds, scaled upward through 15 orders of magnitude of pressure and temperature. The iron forms droplets in the sky of a world that never became a star for the same reason water forms droplets in the sky of a world that orbits one. The physics is patient. It does not require stars or planets or sunrises to run its course, and yet the result is strikingly particular. The spectrum of a brown dwarf at a given temperature is not a smooth curve that could belong to any hot object. It is a shaped thing, notched and deepened by the specific molecules that have formed in its specific chemistry at its specific pressure and temperature profile. Water absorbs here at these particular wavelengths, methane absorbs there, carbon monoxide absorbs at its own wavelengths. The spectrum is a fingerprint of an atmosphere, and that atmosphere is a fingerprint of a temperature, and that temperature is a fingerprint of a mass and an age. To read a brown dwarf spectrum carefully is to read its history, not all of it, but the chapter that concerns how long it has been cooling and from what it began. The instruments that have read these spectra have been sensitive infrared telescopes, most working from space or from high dry mountain sites where the Earth's own atmosphere absorbs as little as possible of the incoming signal. The spectra come back as series of measurements, the brightness of the object at many individual wavelengths, plotted against those wavelengths, and the shapes they form are immediately recognizable to those who study them. The deep band of methane at 1.6 microns, the broad water vapor absorption between 1 and 1.3 microns, the flattening of the spectrum across wavelengths where ammonia would absorb in the coolest cases. These shapes are the vocabulary of these atmospheres, and they have been read in dozens and eventually hundreds of objects spread across the solar neighborhood, each one its own slow world with its own iron clouds or methane chemistry or ammonia threshold, each one rotating quietly in the dark. The clouds of one particular brown dwarf, observed over the course of a night, show a pattern of variability that changes measurably even over the span of a few rotations. In the first few hours of observation, the light curve has one shape, a broad rise and fall over a period of about 8 hours, suggesting a single dominant, large cloudy region. By the following night, the shape is slightly different. The peak has shifted, the amplitude has changed. Something in the cloud layer has reorganized, redistributed, thickened or thinned in a part of the sky that was not as prominent the night before. The brown dwarf is not the same from one night to the next in its atmospheric detail, even as its fundamental properties, its mass, its temperature, its rotation period remain unchanged. This is the thing that makes brown dwarf weather feel recognizable even from such a distance. Not the iron clouds, which are alien in composition, not the methane chemistry or the absence of a sun, the variability, the drift of weather systems across a world that is quietly turning, the way the light changes in a pattern that is regular in its period, but not in its detail, a rhythm with texture, a clockwork that is also alive. Jupiter has the same quality. Saturn has it. Earth has it most of all, from any distance at which its daily rotation could be resolved. The rotating world, carrying different cloud structures into view with each turn, is a pattern that shows up at planetary mass and at the lowest stellar mass and everywhere between them. The scale changes. The molecules in the clouds change. The source of the driving energy changes. But the rotating sphere wearing dynamic weather is a form that the universe returns to again and again, across ranges of mass and temperature that span everything from the inner planets to the coolest inhabitants of the interstellar dark. The atmosphere of a brown dwarf is almost impossible to visit in imagination without distorting it into something too familiar. It is easy to reach for the imagery of a storm at night, of clouds crossing a dark sky, of metallic rain, but this is not quite right. The iron droplets do not fall through open air in any sense that the word conveys. The pressure is too high, the scale too large, the whole column of gas too deeply mixed and stirred by convection for any simple picture of rain and clouds and gaps to hold. What is actually happening in the atmosphere of a brown dwarf is a three-dimensional, continuously evolving distribution of mineral condensates suspended in turbulent gas embedded in a global convective flow that extends from the interior outward, all of it responding to the slow cooling of the world from within. The simplification to clouds and weather is useful because the physics is genuinely the same physics. The picture, at the level of sensory imagination, needs to be held more loosely. What can be held without distortion is the scale of the time involved. The iron cloud layer of a warm brown dwarf has been present since not long after the object formed, condensing and evaporating in its slow cycle for hundreds of millions or billions of years. It will remain present until the world has cooled past the point where iron can condense in the upper atmosphere, which will take many more hundreds of millions of years. The methane chemistry that follows will persist for billions of years after that. The ammonia threshold, if and when it is crossed, will persist for longer still. Each stage of this atmospheric life lasts for stretches of time that encompass the entire history of complex life on Earth and leave room for more. The brown dwarf turns. The iron clouds drift in the hydrogen air, thick in some regions, thin in others. The convective currents rise and fall. The warmth that was gathered at the moment of formation seeps outward through the mineral haze in wavelengths of light that no human eye has ever evolved to see. In a narrow band of infrared wavelengths, at just the right temperature, the iron droplets absorb a portion of that light and re-emit it at slightly different wavelengths, contributing to a spectrum that carries in its shape the complete current state of a world billions of years in the making. The world turns, and the clouds with it, and from the only vantage point from which these things have ever been seen, the instruments of patient observers at vast distances, the light rises and falls in a slow wave, a few percent brighter, a few percent fainter, as each cloud region completes its long circuit and returns. The wave repeats. Every few hours, it repeats. Through the night, it repeats, and through the nights that follow, with small variations in shape as the clouds evolve, and through the months and years of continued observation, the same fundamental rhythm persists. The rotation of a world in the dark, carrying its iron weather with it, leaving a faint record in the light that eventually, across light years of distance, reaches an instrument and is measured and set down. There is no sound, there is no sun, there is only the turning and the slow outward drift of ancient warmth through mineral clouds, and the long patience of a world that never quite became a star, but has been something of its own kind for longer than the earth has been solid, in weather that no season has ever interrupted, under a sky that has never once been bright. The light curves grow quieter as the brown dwarf cools. A very old, very cold object, down to 500 Kelvin or below, shows less dramatic cloud variability. The chemistry of its atmosphere is different. The condensate layers are deeper and more stable in some respects. The convective vigor has diminished somewhat, as the interior heat source has weakened over the long years. The variations are still present, still measurable, but they are subtler. The amplitude is smaller. The signal requires longer integration, more sensitive instruments, more careful removal of the noise in the data. The coldest known brown dwarfs are very faint. Their peak emission is in the mid-infrared wavelengths of 5 to 15 microns, where Earth's atmosphere absorbs strongly and where ground-based observations are difficult. From space, at the right infrared wavelengths, these objects appear as faint points, distinguishable from background sources, mainly by the specific pattern of their colors across different infrared bands, too faint in one band, brighter in another. The ratio of their brightnesses forming a pattern that marks them as very cold and very nearby, rather than very distant and intrinsically luminous. The cold has been deepening in these objects since they formed. It will continue deepening. Billions of years from now, a brown dwarf that currently sits at 500 Kelvin will have cooled to temperatures lower still, and the objects that are already near 300 Kelvin today, those extreme, ancient cases will have cooled toward temperatures where the distinction between a very old brown dwarf and a very massive and very old planet begins to blur in ways that no current definition can fully resolve. The boundary between the two was never sharp at the cold end. It was always a matter of formation and mass rather than appearance, and as these objects cool, their appearance becomes less and less able to carry that distinction. The iron clouds of the warmer ones drift on. The methane fills the spectra of the cooler ones. The ammonia appears in the coldest cases, faint and cold and slow, in a sky that has been dark since before the first fish ever breathed. And somewhere, in infrared light invisible to any unassisted eye, the slow wave rises and falls as each of these worlds completes another turn, another rotation counted off in the dark, another few hours of ancient warmth reaching outward through clouds of iron and silicate and methane, another small record laid down in a light curve measured by a telescope that was itself built on a world warmed by a different kind of fire, a star that did sustain its fusion, that did hold the 10 million Kelvin core long enough to burn steadily for billions of years, that gave its light generously to a planet with oceans and life, and eventually instruments sensitive enough to catch the much quieter warmth drifting across the dark from these other worlds. The brown dwarf turns. The cloud layer thins in one quadrant, thickens in another. The infrared signal shifts by a few percent. The wave completes. Then it begins again, in the same dark, in the same silence, with no witness required and no sunrise coming. The iron clouds, patient and slow and ancient, carrying the last warmth of a world that almost burned. An L-dwarf hangs in the dark between stars, and its light is the color of cooling iron, not red like a fire, not orange like an ember, something deeper than either of those, a warm, heavy glow that sits at the far edge of what the eye could register, if the eye were close enough, and then spills past it into the infrared where human sight ends and the instruments begin. The object's surface temperature runs somewhere around 2000 Kelvin. That is hot enough to melt most metals on Earth. And yet against the scale of stars, against the 10 million degree hearts of ordinary suns, that temperature is a low, slow smolder, a warmth that has been fading since the object first formed, pressed by its own gravity into a sphere barely wider than Jupiter, and left to cool through all the long quiet time that followed. The L-dwarf class is where the spectral sequence of brown dwarfs begins. It is the warm end of a long dimming corridor. Objects in this class carry their temperature written in the structure of their light. Mineral clouds drift through their upper atmospheres, particles of iron and silicate suspended in hydrogen gas, thick enough to redden and obscure the outgoing glow, the way a dusty window colors the light that passes through it. The infrared spectrum of an L-dwarf carries the fingerprints of metal hydride molecules, narrow absorption bands where specific compounds have intercepted specific wavelengths. It carries the signatures of sodium and potassium, neutral alkali metals, diffusing through the high atmosphere, broadening into wide, shallow troughs that darken the spectrum across a range of colors. All of that together, the cloud opacity, the metal hydride lines, the alkali signatures, reads as a warm, reddened glow in the near infrared, and it identifies the object as something sitting in the upper range of the brown dwarf sequence, still warm enough for iron to float in its sky. The corridor descends from here. It descends slowly across millions and billions of years. A brown dwarf in the L-dwarf range is not at rest. It has been cooling since the first moment of its existence, since the gravitational contraction of its early life began converting the potential energy of its own collapse into heat. And that heat has been leaking outward ever since, photon by photon, into the interstellar space around it. There is no nuclear furnace in the core to replace what is lost. There is nothing to arrest the descent, and so the object cools, and as it cools, its atmospheric chemistry shifts, and the clouds that gave the L-dwarf its characteristic reddened glow begin, over immense spans of time, to change their behavior. Iron cloud particles require a certain temperature to remain suspended in the upper atmosphere. Below that temperature, they begin to settle. They sink through the pressure levels of the atmosphere, the way sediment sinks through still water, gradually, continuously, descending out of the photosphere into deeper, hotter layers where the temperature is still high enough to keep them in their particulate form. The upper atmosphere clears. The thick mineral haze that colored the L-dwarf spectrum begins to thin and then to lift entirely out of the observable layers, leaving behind an atmosphere that is more transparent in certain wavelengths than it was before. The object grows bluer, not because it is heating up, but because the obscuring layer has gone. This transition is one of the more striking details in the whole story of brown dwarf cooling. The object does not smoothly and gradually redden into darkness as it ages. At a temperature of around 1400 Kelvin, something more abrupt happens. The clouds sink, the color shifts. The near-infrared spectrum changes character almost as continuously over what is, in cosmic terms, a narrow temperature range, and on the far side of that shift, the object belongs to a different spectral class entirely. That class is the T-dwarf. A T-dwarf sits in a temperature range from roughly 1300 Kelvin down to around 500 Kelvin. Its defining chemical signature is methane. Below about 1400 Kelvin, methane becomes stable in a brown dwarf's atmosphere. It survives in the upper layers without being broken apart by the heat. And once it is there, it absorbs outgoing radiation at specific near-infrared wavelengths, at 1.6 microns, at 2.2 microns. Those wavelengths go dark in the spectrum, and in their place the methane absorption bands appear, deep and distinctive, unmistakable once seen. The T-dwarf spectrum does not look like the L-dwarfs. The reddening from cloud opacity is gone. The methane bands have replaced it, and the object in certain infrared channels is noticeably bluer than the cooler L-dwarfs that preceded it. Water vapor deepens its absorption signatures in this range as well. Carbon monoxide leaves its trace. The spectrum of a T-dwarf is a crowded record of molecules, each one present because the temperature has fallen into the range where that molecule can form and persist, each one removing a specific slice of the outgoing light and leaving its mark as a dark band in the spectrum.
In a T-dwarf sky, if sky is a word that applies, the iron clouds are gone from the heights. The upper atmosphere is cleaner. What remains above is hydrogen and helium, and the molecular compounds that have condensed in the cooler layers. Water ice crystals forming where the temperature has dropped far enough. Traces of ammonia beginning to appear as the object grows cooler still, each new compound a marker of how far along the descent has gone.
The T-dwarf class spans a wide temperature range. At the warm end of it, the object still glows faintly in the near infrared, still radiates enough heat that sensitive instruments can detect it from moderate distances. At the cool end, around 500 Kelvin, the glow is fainter. The peak of emission has shifted further from the visible. The object is darker in every band the eye could reach, and its light has moved deep into the infrared, into wavelengths that require detectors cooled to near absolute zero to measure cleanly. Below 500 Kelvin, the object crosses into a third class. The Y dwarf is the end of the sequence. It is the coldest, faintest, most dimly radiating category of brown dwarfs known, and the objects within it have cooled to temperatures that no longer have any reference point in stellar physics. The warmest Y dwarfs sit at around 500 Kelvin. The coolest known examples are colder than that. Much colder. Ammonia condenses in the atmospheres of Y dwarfs, producing new absorption features in the near infrared that are distinct from the methane signatures of the T class. The peak of the object's emission continues to shift into the mid-infrared, into wavelengths measured in tens of microns, far from anything the human eye registers as light. The object radiates, still. Heat always finds a way outward, but the wavelengths it favors are so long and the total output so faint that detecting a Y dwarf requires instruments of considerable sensitivity pointed at a patch of sky for considerable time. There is something in this that asks to be held quietly. A Y dwarf is still a massive object. It contains tens of times the mass of Jupiter, packed by electron degeneracy pressure into a sphere roughly Jupiter's size. Inside that sphere, the temperature rises with depth, from the cool photosphere inward through progressively hotter layers, down toward a core that remains warm long after the surface has grown cold. But the surface, the photosphere, the layer from which light finally escapes into space, that layer in the coldest Y dwarfs has cooled to temperatures near 300 or 400 Kelvin. 300 Kelvin is close to the temperature of a warm day in summer. It is close to the temperature of a human hand. The light leaving a Y dwarf at 300 Kelvin is the kind of light that any warm object emits, a table, a wall, a body resting in a dark room, the kind of infrared glow that no human eye has ever been built to see. Because on Earth, every surface produces it, and the eye long ago learned to ignore it in favor of the reflected light of the sun. A Y dwarf produces nothing else. No reflected sunlight, because it circles no star close enough to illuminate it significantly. No nuclear glow, because fusion stopped long ago, if it ever truly started. Only this, the slow, patient outward leaking of heat, accumulated billions of years ago, carried outward through convective currents, and eventually released from the photosphere as mid-infrared radiation that drifts away through interstellar space and arrives, eventually, at a telescope. The spectral sequence of LT and Y dwarfs is not a catalog of different kinds of objects. It is a single kind of object photographed at different moments in a process that has no end before the deep future of the universe. An L dwarf will one day cool into a T dwarf. A T-dwarf will one day cool into a Y-dwarf. A Y-dwarf will continue to cool, growing fainter and fainter, its emission peak sliding further and further into wavelengths that require ever more sensitive instruments to detect. The sequence is a timeline made visible by the diversity of ages and masses among the objects that have formed across the history of the galaxy. Brown dwarfs formed early have had billions of years to cool. Brown dwarfs formed recently are still warm. The range of temperatures visible in the sky at any moment is a record of all that cooling history, spread out and present at once, the way a beach holds sand of every age, grain by grain, unsorted from one another, the old and the new, lying together in the same quiet stretch. The L to T transition is the sharpest boundary in this sequence. At that boundary, the cloud clearing and the methane onset and the color reversal all happen within a narrow temperature range, producing a population of objects that look remarkably different, despite being at nearly identical temperatures. Two brown dwarfs at 1400 Kelvin might show very different spectral characters, depending on exactly where their clouds sit, how patchy their coverage is, how far along the clearing has progressed. The transition is not a clean line. It is a zone, and within that zone, the diversity of appearances is greater than anywhere else along the cooling curve. The objects do not all cross it at the same pace or in exactly the same way. Then the transition is complete, and the T-dwarf emerges on the other side, clearer skied, methane marked, bluer than the L-dwarf it used to be, and the cooling continues. There is a particular object that reaches the far end of this sequence. It was identified from data collected by a space-based infrared survey, a telescope in orbit mapping the entire sky in infrared wavelengths, searching for the faint signatures of cold objects that no ground-based telescope could easily detect through the thermal glow of Earth's own warm atmosphere. That survey was called the Wide Field Infrared Survey Explorer, and among the thousands of sources it cataloged was a point of mid-infrared light in a part of the sky marked by the coordinates 18 hours, 28 minutes of right ascension, and 26 degrees, 50 minutes of declination, designated in the notation of the survey, WISE 18, 28 plus 26, 50. The object appeared in the survey data as a faint detection in certain infrared bands and an absence in others. Its colors, the ratios of its brightness across different wavelengths, were unlike those of ordinary stars, unlike those of galaxies, unlike almost anything else in the catalog. The colors placed it at the cold end of the Y-dwarf sequence. Temperature estimates from the early analysis suggested values close to 300 Kelvin. Some estimates came out lower still. A brown dwarf at 300 Kelvin, drifting somewhere between several tens and a few hundred light years from Earth, floating alone in the dark of the galaxy, radiating its warmth in wavelengths that human eyes cannot see, carrying within it tens of times the mass of Jupiter, covered in an atmosphere where ammonia clouds may have begun to form. This is one of the most extreme members of the brown dwarf population known at the time of its identification. It sits at one end of a sequence that began billions of years ago as something much warmer and has been cooling ever since through every stage of that long descent. The light that WISE 1828 plus 2650 sent into the detectors of that infrared telescope had been traveling for some span of years or decades. It is impossible to say exactly, without a precise distance, before arriving in orbit around the Earth and being converted into a signal, a data point, a faint excess of brightness in certain mid-infrared channels that a computer algorithm flagged as unusual and a human astronomer then examined more closely. The examination confirmed what the colors suggested. The object was cold. It was a white dwarf. It was among the coldest things in the sky. It is still out there, cooling still. In the years that followed that identification, the question of how cold a brown dwarf could be, how far the white dwarf sequence extended before it merged into the population of free-floating planets, themselves rogue worlds, ejected from forming solar systems and drifting dark through the galaxy, remained open. The boundary between the coldest white dwarfs and the largest free-floating planets is not a clean line any more than most boundaries in astronomy are. At some point, the mass and composition cease to distinguish the object from a planet. At some point, the temperature falls low enough that the word dwarf loses its meaning. The sequence simply continues, growing fainter, growing colder, following its uninterrupted descent through every temperature the universe allows, limited only by how old the galaxy is and how long the coolest objects have had to radiate away their heat. Billions of years from now, the warmest L dwarfs visible in the sky today will have cooled through the T dwarf phase and on into the Y dwarf range, joining the population of cold objects already there. Billions of years after that, even the warmest of today's T dwarfs will have crossed into Y dwarf territory and cooled further still. The sequence is not static. It is a river running in one direction, slowly, without end in any time scale relevant to biology or civilization or the observable history of stars. The spectral classification system, LTY, is a set of labels placed on a continuum, the way one might mark a thermometer at intervals to help read it. The labels do not create the categories. The categories arise from the chemistry, from the specific temperatures at which specific compounds condense and specific molecules become stable and specific cloud layers form and clear. The letters are human, a convenience. The physics underneath them is not. And reading that physics from a distance, from the faint signal carried across light years and measured in the near-infrared and mid-infrared bands of a space-based telescope, is something that happened within the span of a human lifetime. The first confirmed brown dwarfs were identified in 1995. The wide dwarf class was not formally established until the Wide Field Infrared Survey Explorer survey began returning results in the early 21st century. A WISE 1828 plus 2650 was announced as an extreme wide dwarf candidate within a few years of the survey's launch. The span from no confirmed brown dwarfs to a catalog of objects cooler than the human body is short, measured in decades. The universe, meanwhile, has been making and cooling these objects for as long as it has been making stars. There is a particular quality to the image of WISE 1828 plus 2650 in the survey data. It is not spectacular in the way that images from large optical telescopes can be. There is no nebula glowing around it, no disk of dust catching scattered light, no companion star casting illumination across its face. It is a point, a single point of mid-infrared brightness against the dark background of the surveyed sky, distinguished from the surrounding sources only by the specific ratio of its brightness in one wavelength band versus another. How the ratio encodes everything: the temperature, the atmospheric chemistry, the presence of methane and ammonia, the coolness that places it among the most extreme members of its class. The information is there, written in the numbers, readable only because enough is understood about the physics of cool, dense, slowly cooling spheres of hydrogen and helium to interpret what those numbers mean. 1 point of light, or rather 1 point of warmth, a warmth so faint that it does not register as light at all in any ordinary sense. A warmth that has been diminishing for billions of years, leaking outward from a core that was never hot enough to truly burn, through an atmosphere of ammonia and methane and water vapor, through layers of cool gas where no sun rises and no wind is driven by anything other than the object's own interior heat, out into the interstellar medium where it spreads and dilutes and eventually becomes indistinguishable from the background glow of the galaxy. The object does not know it is cooling. Nothing in the description implies awareness or intent. The cooling is simply what happens when there is no energy source to replace what is lost, and what is lost is carried outward by photons that leave the photosphere and travel in every direction at once, into the dark, each one carrying a small fraction of the accumulated heat of billions of years of slow gravitational contraction and brief early fusion, each one thinning the remaining warmth by an imperceptible amount. Across enough time, even that slow loss becomes significant. Across billions of years, it is everything. The L dwarf glowing with the warmth of mineral clouds, the T dwarf clearing into methane-scented transparency, the Y dwarf barely warmer than the ground on a summer afternoon, drifting between the stars. All three are the same kind of object. All three are snapshots of the same process, caught at different stages, each stage following inevitably from the one before it. The whole long sequence driven by nothing more and nothing less than the patient outward flow of heat through matter. A brown dwarf begins with a collapse, a cold, dense knot of gas and dust falling inward under its own gravity, growing hotter as it contracts, glowing briefly with the warmth of that contraction, burning through whatever small store of deuterium it contains in those first few million years, and then settling into a long, uninterrupted cooling that will outlast every civilization that has ever kept records and every star currently visible in the night sky. It reaches the L dwarf phase, warm and cloud-shrouded. It reaches the T dwarf phase, cooler, clearer, wearing its methane signature like a change of atmosphere. It reaches the Y dwarf phase in a kind of deep, geological cold, not frozen, not dead, still radiating, still conveying heat outward from core to surface, through the slow rolling of convective currents, but dim, very dim, and growing dimmer. The sequence is a record of time. An old brown dwarf is cold, a young one is warm. The temperature read from the spectrum is an age, not precisely, because the mass also matters, and different masses cool at different rates. And a more massive brown dwarf cools more slowly than a lower mass one at the same age, but in a general sense, a Y dwarf has been cooling longer than an L dwarf, and carries in its cool photosphere the record of more time having passed. Y's 1828 plus 2650 at 300 Kelvin carries the record of an enormous span of cooling. Whatever its mass, whatever its precise age, it has been losing heat for long enough to have descended from the warmth of an early brown dwarf, warm enough to sustain deuterium fusion for a few million years, warm enough in its infancy to glow at temperatures comparable to a small star, all the way down to temperatures where ammonia condenses and the emission peak has long since left the near infrared and settled into the mid-infrared, where only the most specialized instruments can find it. That descent is not dramatic. There is no moment in the cooling of a brown dwarf when something suddenly changes, no event that marks the passage from one spectral class to the next, in the way that a stellar explosion marks the end of a massive star's life. The L to T transition is abrupt only by the standards of a process that unfolds across millions to billions of years. On any human timescale, the change is invisible. The brown dwarf simply cools, day by day, year by year, in amounts so small that no instrument could measure the change from one year to the next. And over the immense spans of astronomical time, those immeasurable daily losses accumulate into a journey from one end of the spectral sequence to the other. The cooling is quiet. There is no sound in interstellar space, no medium to carry one. The object drifts. It rotates. Most brown dwarfs spin relatively quickly, completing a rotation in somewhere between a few hours and a couple of days. And as it rotates, the cloud patterns in its atmosphere turn through whatever view a distant observer might have, producing the slow periodic brightening and dimming in its infrared light curve that was described in measurements of objects at intermediate temperatures. For white dwarfs, even that faint signal becomes harder to detect. The infrared brightness is so low, the variation so small relative to the noise in any measurement, that characterizing the cloud structure of a white dwarf requires long observations with large, cold, carefully calibrated instruments. And yet those measurements have been made, not for every white dwarf, not in every detail, but for enough objects and in enough wavelength bands that the picture has become reasonably clear. Brown dwarfs at the cold end of the sequence have patchy dynamic atmospheres, just as their warmer counterparts do. They have cloud structures that evolve over time. They rotate, they cool. They are, in every way that physics applies, ordinary objects bound by the same equations, built from the same materials, following the same rules as everything else in the universe. The extraordinary thing is only where those rules have carried them to temperatures so low that they have left the domain of astronomy and entered the domain of meteorology, with atmospheres more closely comparable in temperature to the surface of a rocky planet than to the photosphere of any star. The sequence from L to T to Y is the story of that journey. It is a journey made without any destination, because there is no endpoint the object is approaching, no state toward which it is being drawn beyond the progressive loss of heat to the surrounding space. The universe around a cooling brown dwarf is very cold, a few degrees above absolute zero in the interstellar medium, colder still in some regions. Against that background, even a white dwarf at 300 Kelvin is warm. Even a white dwarf will continue to radiate. The temperature difference between the object and its surroundings is what drives the flow of heat outward, and as long as that difference exists, the flow continues. The universe expands. The background cools toward absolute zero. The brown dwarf cools with it, never quite catching up, always a little warmer than its surroundings, always losing a little heat, always moving, infinitesimally slowly, down the scale of temperatures toward a cold it can approach, but never reach on any time scale that has a name. That is a long kind of patience. The spectral sequence holds it all. The all dwarf's warm, cloud-reddened glow, the T dwarf's clear methane signature, the Y dwarf's faint mid-infrared warmth, barely detectable against the cold sky, carrying in the ratios of its infrared brightnesses the record of how far it has come and how far it has yet to go. Y's 1828 plus 2650 sits near the cold end of what has been measured. Whether colder objects exist, whether the Y dwarf sequence extends to even lower temperatures before it meets the population of free-floating planets and becomes indistinguishable from them, is a question that the instruments of the early 21st century have only begun to answer. The answer is probably yes. Probably the sequence extends further. Probably there are objects cooler than 300 Kelvin drifting through the galaxy, too faint to have been found yet with existing surveys, waiting for a telescope, cold enough and sensitive enough and patient enough to find them in the dark. They would look like nothing visible to the eye. They would not look like stars. They would not glow like embers or shine like planets catching sunlight. They would be warm patches in the mid-infrared, small, spherical, slowly rotating, patchy with cloud, cooling at a rate too slow to measure from year to year. And if something with the right eyes were close enough to see them, they would look like spheres of low, even warmth in an otherwise cold universe, like a stone carried indoors from the cold and set down on a table, still holding the memory of the warmth that was given long ago. Not all heat is fire. Some heat is just what remains, the slow, patient remnant of energy accumulated in an ancient collapse, leaking outward through billions of years of uninterrupted cooling carried past iron clouds and methane layers and ammonia hazes, past the boundary of the L-dwarf class and the T-dwarf class, and down into the long, quiet domain of the Y, where the emission is faint and the colors sit deep in the mid-infrared, and the classification system runs out of letters, and the object continues anyway, cooling past the edges of the known, carrying its diminishing warmth into the dark. Y's 1828 plus 2650 is out there now. It is cooler tonight than it was when the photons that identified it left its photosphere. It is cooler than it was when the Wide Field Infrared Survey Explorer was launched, cooler than it was when the survey data was first analyzed, cooler than it was when the paper announcing its discovery was written, and cooler than it will be named in any catalog for as long as any catalog exists. The difference from one year to the next is unmeasurably small. The difference across a billion years is the difference between a warm L-dwarf and a cold Y-dwarf. It has already made that journey once. It will continue making it, measured in temperatures too small to name, in wavelengths shifting so slowly that no human lifetime could detect the shift, until the sky around it has cooled to meet it, and the difference between the object and the universe it drifts through has narrowed to something too small to read, for now the difference is there. 300 Kelvin, give or take, in the mid-infrared, a faint point of warmth in a cold sky, a sphere of dense, slowly cooling hydrogen and helium, carrying the memory of its own formation in the residual heat of an ancient collapse, drifting somewhere in the galaxy, at a distance the light has been crossing for years.